Hi everybody. Hello. Am I audible and visible? Quickly go ahead and let me know in the chat box if I am audible and visible so that I can start with the session. Hello guys. I believe I am. Yes. So hello everybody. As I always say, Andariki Namaskaram Ellargu Swagatam. This is me, your master teacher Nabamita Ma'am, and today we are here for yet another amazing session of P Block. You know, I really thought that maybe we should be able to finish the whole P Block in just 2 sessions. But then when I started, teaching, and when I saw that this is actually a very important chapter, and the fact that it is a big chapter, I wanted to do justice. So I don't think that today also we will be able to finish it because there is a lot of information, a lot of data that I want to be able to give it to you. Maybe later on, yes, once we have finished the chapter in detail, later on you should not come and tell me that, ma'am, you did not teach us in detail only. Yeah, so that should not be the case. That is why I'm going to take these sessions in detail, absolutely. And then later on we can come back and maybe we can try and finish this session in about 2 to 3 hours. But later on, not today. Today we are going to solve it in detail, and today we are going to take a look at the carbon family, everybody. So are you all with me? Thank you so much, Nabila. Hi, Narayana. Hi, Shriya. Yes. Oh my God. Hi, Talari. Hello. I am much better. Although my throat still pains. So I am having all that adrak wali chai, and today itself, since morning I have had 4 cups of tea just because my throat still pains. But anything for you guys, yes. Whenever I feel a little better, I think I should take the session, and I am here to take the session, everybody. Yes, thank you so much. Hi, Godfather. Hello. Hi, Ashia. Hello, Ram Vidun. Very good evening. And like I always say, Andariki Namaskaram, Ellargu Swagatam, isn't it? So I hope that you all are doing great, and today we are going to start with the carbon family. Are you all ready? By the way, guys, carbon family, please do focus a little bit more because this is the very basic of your organic chemistry, right? Yes. So I need you all to focus up in today's session, and also please sit with a pen and paper. Yes, pen and a paper so that you can write down the notes and you can have it right at your fingertips just before your exam. You don't have to go all bonkers and crazy that, where's my notes? You don't have to do all of that. Okay. All right. P block element is removed from NCERT or board exam, bacha. Please be very careful, everybody. P block, this is removed from board exam. Removed from board exam. Okay. Not from NTA syllabus. Not from your NTA syllabus. Okay. Yes. This is removed from board exam, but it will come in JEE. It will come in JEE exam and NEET exam. So please don't be under the false impression that a P block is not going to come. No, it's a very important chapter. Group 13 to group 18, it is divided into 2 years. In your class 11th, you have group 13 and group 14. Whereas in your class 12, you have the group 15 to group 18. So please do not miss out on it. It's an important chapter. You do get a lot of marks from this chapter in your JEE and NEET. All right. Yes. So let's start, everybody. Now, everybody. If you come to this periodic table, yes, if you come to the periodic table, group 14, today we are going to talk about group 14. And how do we remember group 14, everybody? Group 14 can be remembered as, there is a very chotu mnemonic. Okay, what do you say? You say that chemistry sir, not ma'am, chemistry sir, okay, chemistry sir gives snappy problems, okay, gives snappy problems. All right. Yes, but chemistry ma'am gives jujupy stuff. Isn't it? Chemistry ma'am gives you jujupy stuff. Chemistry sir gives you snappy problems. That's how you remember it. C for chemistry, C for carbon. Sir is silicon, germanium. Then you have what? Then you have tin and you have lead, right? And just like the group 13 elements, okay? Okay, that is also nice. Cute sister got snack pudding. Yes, that is also fine. But however, we remember it as chemistry, sir gives snappy problem. Whatever you want to say, you can always make your own mnemonics, guys. Always make your own mnemonics because that gets stuck in your mind more than anything else, right? Now, just like the previous group that we studied, the previous group was boron family, if you remember. Now, in the boron family also, do you remember that there was this one, Germany, it seems, not Germany. What is it? Chemistry, sir, gives. G for gives, G for germanium. Germanium is a metalloid. Do you remember? I told you. Yes. What was it? Goats are silly aunties. Goats are silly aunties. So this is your goats. Germanium. Germanium is a what? It is a metalloid. Correct? So anything that is above metalloid, these two are non-metals, the chemistry and the sir, that is carbon and silicon, they are non-metals. Germanium is a metalloid and the tin and the lead, they are metals. Right, everybody? Is this clear? Good evening, Chalukya. Good evening. Yes, welcome to the session. Is this clear, everybody? Yes? Are you understanding? Sai, I'll tell you all about that in the session at 8 p.m. Okay, not now. Now, please focus in the session. Please focus in the session. Then later on, you won't understand and you'll be like, ma'am, didn't understand, ma'am. So listen, yes? Alright, so what are the things that I have told you till now? I have told you, first of all, how do you remember it? How do you remember it? You remember it as chemistry, sir gives snappy problem, or cute sister got snack as pudding. Yes? Alright, everybody. These are the things that you remember is. Now, this last one that you see, okay, this last one, do you know what is this? This is your, everybody, it is a synthetic radioactive element. Alright, this is a synthetic radioactive element. So we basically don't have to talk about it so much. All right. Yes, we don't have to talk about it so much. Cool, everybody. Now, this is what? Carbon, silicon, germanium, and then tin and lead. Now, you can clearly see that germanium is a metalloid. Above metalloid is always non-metal. Below the metalloid, these are metals. Agreed, everybody? Clear? Clear? All right. Yes. Now, again, in the previous group, that is the boron family, we had noticed that in the boron family, group 13, what was the general electronic configuration? General electronic configuration was NS2NP1. But can I again say it is NS2NP1? No, this time it is NS2NP2, but choose. What is it? NS2NP2. All right. Yes. So let's write down. Let's write down. Do you remember how to, do you remember the mnemonic for noble gases? Because you will again have to use it, right? What was it? It was Hina, Nina, arrived, yes, arrived, Karina, Xeroxed, Ranbir. Do you remember? Yes. So Hina, Nina, argon, that is helium, neon, argon, krypton, xenon, and radon. I hope you remember this, right? Yes, this was the one for your, what was it? These were the noble gases, the mnemonics for noble gases. So you always have to write the noble gases, and then what do you write? And then you just start writing this NS2, NP2, because this is the general electronic configuration. So what will it be? For carbon, it will be 2s2, 2p2, right? Yes. Then for silicon, what is it going to be? 3s2, 3p2. Am I right? But for germanium, this is the third period now. This is, sorry, not the third period. This is the fourth period. Fourth period, what do you have? You have 3D series coming up now. D orbitals are introduced. So what do we write? Whenever D orbitals are introduced, it will be N minus 1D. It cannot be 4D10, but it is going to be 3D10, 4S2, 4P2. Make sense or nonsense, everybody? Write it down. Keep chatting, everybody. But what do you want me to chat? What do I want you to chat? Yes, no, talk to me. Talk to me. Interact with me. Let me know what are your doubts. Just so that I can make it clear for you right away, right now. You should not be stepping out of the session and have doubts, right? Right now, clear it all, okay? 3D10, 4S2, 4S2, 4P2. Clear? All right. Then what will happen? Obviously, here also we will have a D series. D orbital will be here as well. So 4D10, 5S2 and 5P2. Making sense? Making sense? Making sense, everybody? But now, the moment we come to PB, what will we have? This time, we will also be having the F series, isn't it? F orbitals are going to be introduced, and that means that whenever F orbitals are introduced, what do we know? We know that it is N minus 2F, isn't it? So basically, now what will happen is, of course, we will write it as 6S2 and 6P2. But here what will happen? You will write as 4F14, 5D10, 6S2, 6P2. Right, and for the last one, my dear students, what will you write? Here you will write it as 5F14. Yes, right. After that, what will you write? 6D10 and then 7S2, 7P2. Am I clear? So this is the general electronic configuration and the electronic configuration of the whole carbon family. Yes, everybody, this is clear, guys. This is clear, correct? Okay. Now coming to a little bit towards the NCERT, because I know I kept telling you that for inorganic chemistry, NCERT is very important. NCERT is very important. So let me tell you a little bit about what is written about this family in your NCERT. In your NCERT, you will find that carbon, yes, carbon in its elemental state, carbon in its elemental state is found, or it exists as what? Coal, right? Then you will read about graphite, correct? Yes, then you will read about diamond. Now, graphite and diamond are also called as allotropes, and about that we will read in some time, don't worry, right? This is basically your elemental state. That means, what do we mean by elemental state? But choose elemental state, but choose single. Yes, not ready to mingle. Of course, it will be ready to mingle, because we will see that in some time. Right away, we will see that it is also found in combined state. Now, how do you find it in combined state? In combined state, you will see that combined state, okay, combined state also carbon exists. But tell me something, everybody, combined state, how you, what do you think that it will exist as? Everybody knows organic chemistry, the whole of organic chemistry. Where does it start from? Hydrocarbon, but choose. So yes, in combined state, you will find it as hydrocarbon, right? Then what are the gases that you will find? You will find it as carbon dioxide, carbon monoxide, and then also carbonates, metal carbonates, isn't it? Metal carbonates as well. So this is how carbon exists. Now, not only that, everybody, not only that, let me also tell you that carbon exists in 3 isotopes, or there are 3 isotopes of carbon. So let's write that down, everybody. There are 3 isotopes of carbon, okay? 3 isotopes of carbon. Can somebody tell me what are these 3 isotopes of carbon? Yes, there is C14, C13 and C12. So basically C12, C13 and C14, right? Now C14 is used for radioactive dating. Have you heard that many a times, in our newspapers, you must have seen that this fossil fuel or new kind of dinosaur bones are found and this dates this old, or, people keep telling about that Egyptian pyramid is found and this pyramid is this many years old. How do they figure out how many years old is it? That's done by this radioactive dating. Yes, not that dating that you're thinking of. Not that dating that you're thinking of. What is this carbon dating? You basically find out the date, okay? Find out the year or the date. How old is something? That dating we're talking about. So what did I say? C14, okay? C14 is an isotope with a mass number 14. But carbon, you know what is the atomic number, right? It's written here as well. Carbon has an atomic number of 6, isn't it? But it has a mass number of 14 and that is an isotope. So C14 is used for radioactive decaying, but choose, okay? Radioactive dating, not decaying, sorry, radioactive dating, yes. Like if you want to figure out the date of a fossil fuel, or if you want to figure out the date of a dinosaur bone, or if you want to figure out the date when the pyramid was created, right? These kind of things are figured out from this carbon 14. Basically, you have to use it and then you figure it out. I don't really know how it is exactly done because, to be honest, never read about it, but that just gives me an idea. I will probably read about it. Yes. Okay. Yes. Very good. Half a life period of radioactivity of, yes, Gokul, you are right. Carbon nanotubes, fullerenes are also allotropes. Yes. 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 Fullerene, yes. We will read about it. Don't worry. Don't worry. Don't worry. We will read about it. But carbon nanotubes, carbon nanotubes are actually created from graphite. Yeah. Because, what you call it? Graphite has layered structure, isn't it? So you use that to create a tube and that is called as carbon nanotube. So we will read about it, but Don't jump the story. Don't jump the story. This is a movie. Imagine this is a movie. You have some popcorns and keep writing down your notes. All right. Yeah. Moving on, guys. Then what do we have? We have C12 and we have C13. Acha, by the way, this is radioactive dating, as you can see, right? Yes, what did I write? I wrote here radioactive dating. That means that this is kind of unstable. What is it? This is unstable, but choose this is not very stable, right? However, carbon 12 and carbon 13, these are stable isotopes of carbon. What are these? Stable isotopes of carbon. Cool. All right, everybody. This is understood. This is understood. Great. Now, silicon. We will be reading about silicon as well. And silicons, they exist in the form of silicates, right? And they exist also in the form of silica. What is silica? Silica is SiO2. SiO2 is called as silica. Silicates is SiO4 minus 4. All right. So let's write about silica as well. Okay. Let's write about silicon. What do we have in case of silicon? It exists in the form of, okay. Write that down, everybody. Exists in the form of silicates. We will read about that. Silicates and silica and silicones. All right. Yes, all of these you will find out. All of these you will find out. Silicates are basically SiO4 minus 4. All right. And this is your SiO2. Basically, it's a dioxide. Silica is a silicon dioxide. Cool. Got it? Yes. Now, silicates, where are they present? Glass. Do you know glass? Your window glass, window panes and all of that, yeah? Yes, that glass. Ceramics, yes. In those cases or in those materials, you will find silicates are being used, okay? All right, clear hai? Now, moving on to germanium. Germanium is what? It's a metalloid. I'm pretty sure that you all know that it's a metalloid. And also, have you heard that it is kind of a semiconductor? Have you heard of it? In physics, you must have read about it, isn't it? That NPN junction, semiconductors and all of that you must have read, isn't it? So, germanium is actually used as a semiconductor. And in physics, you must have also read about something called as transistor. Do you remember? Do you remember? Yeah, I'm not a physics teacher, guys. So, I probably might not be able to teach you. And also, I have forgotten. It has been a little more than a decade that I have completed my graduation, although I was a triple major in physics, chemistry and mathematics, but can't really remember anything. You forget when you don't study for so long, isn't it? So what about germanium? Germanium is used as a semiconductor. Yes, used as a semiconductor and transistor. Right? This is something that you have studied, isn't it? Hi, Deepika. Welcome to the session. My health is much better, but my throat still pains. But it's okay. I think I'll get better. No worries. I'm going to try and shout a little less in this session. Right? I'm going to try and shout a little less. Okay. All right. Then I think that's it. So you just have to know about carbon, silicon and germanium. However, about tin and lead, right? About tin and lead, I think you will read about that more in metallurgy because lead exists as PbS. It's an ore. Yes. What is the ore? It is galena. Tin exists as a cassiterite. Cassiterite is basically SnO2. Yes. So these are all ores that we will read about it there is a chapter called as metallurgy. We will read about it in metallurgy. Cool. Now, what do we have to come? Properties. Yes, you guessed it right. So let's come to the properties, guys. And when we come to properties, what do we have to read about? Obviously, atomic radius, ionization enthalpy, and not to forget about electronegativity. What is electronegativity? You remember? Yes. What is ionization enthalpy? You remember. But anyway, I'll tell you. Atomic radius. Okay. So atomic radii, obviously, what do you think? Down the group, the size increases. Everybody knows this. And I believe you remember it from the boron family session as well. P block number 1, part 1 has been already done. If you haven't read it, go and check it out. Okay. All right. So same like this here as well. What happens is carbon has the smallest size. Carbon is on the top. It has an anomalous behavior as well. That means that it behaves slightly different. Slightly you know how you must have seen even in your family, if you are the chottu one, if you are the younger, sibling, you probably do behave a little different, isn't it? You are a little more badmash, you are a little more mischievous, right? You do certain things and then your parents also forgive you, right? Yeah. So basically something like that carbon also does. Carbon is at the top of the family and it behaves slightly different. Why? Because of its small size. So how can you remember? You always have to remember that the first element of these groups, from group 13 to group 18, they behave a little different. Okay. All right. So you see that carbon has the smallest size, then comes silicon, then comes germanium, then comes tin, and then comes your lead, right? In this group, there is no exception in case of the size. However, that did exist in the boron family, if you remember, right? Yes, everybody, in this case, there is no exception, as you can see. Do you see that there is no exception here? All of them are increasing as it is, right? We know that down the group size is supposed to increase and it is increasing. Cool. All right, great. Now, when we come to ionization enthalpy, we know that ionization enthalpy is actually the opposite. It's inversely proportional to the size. As the size increases, ionization energy decreases. Why? Because if the size is bigger, it is easier for us to take away the last electron, because what is happening? The nucleus is not able to look at the electron, right? The nucleus is not able to really, pull it closer to itself, right? Yes, so that is what is happening. However, there is a small chotu exception right here. If you can see, everybody, do you see that SN and plumbum? Yes. Do you see that tin has a smaller size than lead? Tin has a smaller size than lead. Why? What would you say here? What do you think is the answer? Everybody knows this. Everybody knows it. What do you say? You say that this is because of lanthanoid contraction, isn't it? Yes. So this is happening. Why? Because of lanthanoid contraction or poor shielding effect of f orbitals. Correct? Yes, everybody. Lanthanoid contraction, or what we can say, it is because of poor shielding effect of f orbitals. Correct? Yes, this is exactly what we read, isn't it? This is exactly what we read. All right, everybody. You don't have to make any mistake here, guys. Everybody just know this. At the end of the P block, at the bottom of the P block, if there are any exceptions coming, most of the time the answer is because of poor f orbital shielding or sorry, or lanthanoid contraction. Cool hai? Yes? All right. Okay. Now we come to electronegativity. What is electronegativity? If you remember, attraction of bonded electron. There is two atoms, they have formed a bond, and then whoever is pulling that bonded electron closer towards themselves, they are known as electronegative. Now here there is an exception. Here there is a chotu exception. If you can see, everybody, that yes, carbon has the tendency to pull the bonded electron towards itself. So you see that from carbon it decreases. From carbon, it decreases to silicon here. Forget about this, okay? Forget about this. However, you will see that germanium, tin, they have almost equal electronegativity. Almost equal electronegativity. Can you see, everybody? Yes. Can you see, everyone? Right? Do you see it, everybody? Do you see it? So first it is carbon. Everybody. Then what do you have? You have your lead here, okay? And then you see that silicon, germanium and tin, for them it almost remains same. This is the only exception in case of electronegativity that you have to remember. Alright, can you all remember this? Hi Vishwak, hello Arjun, hi Skylar, very good evening guys. Yes, so can you all remember? Please take a note, please make a note and let me know if all of these things are clear to you guys. Is this all clear to you? Quickly write down some la 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 in the chat box if you have understood. Yes, I have covered some properties. I have covered 3 to 4 properties, everybody. 3 to 4 properties are over. So please tell me, is this all clear to you? Shall we move on? Shall we move on, my bachus? Tell me quickly. Tell me quickly. Is it all clear? Yes. By the way, you will get the PDF and you don't really have to remember these, okay? These ionization enthalpy, there is 1086 written, 786 is written, 761. You don't have to remember these values. So I understand if you are telling me that, ma'am, we can't understand, we can't see the number. Don't worry about it. Nobody is going to ask you. It's there in NCERT, but no one is going to ask you about these questions, okay? But anyway, you will be getting the PDF, so don't worry about it, okay? Once you get the PDF, then maybe you can just go through it, or it might be there in your NCERT. Just look at the data, that's it. But no one is, I don't think anybody is going to ask you about this, all right? Cool hai, chalo, all right then, yeah. Okay, moving on, there is another one that I had told you in the previous family as well. Density. How does density increase, bachus? Yes, how does density differ? Let me write that down here. Okay, I'm gonna write that down here, everybody. Density. What about density? We all know that density is directly proportional to mass, because density is equal to mass by volume, isn't it? So density increases, mass increases, density increases. Now we know top to bottom mass is increasing, isn't it? Top to bottom, the mass of the atom is increasing. So tell me something. Don't you think that usually it is supposed to be like this: carbon, then silicon, then germanium, and then tin, and then it will be lead. But have you heard of this sentence that people keep telling you that, ma'am, people keep telling you that diamond is the heaviest substance, diamond is the hardest substance. Have you heard of this? Have you heard of this? Yes. Have you heard of this sentence? So that means that by chance, if you are asked in the exam that if you take graphite or any other allotrope of carbon, then how will the density differ? But if you take diamond, then what will be the density? Well, let me write that down for you. Okay, if by chance, if you take diamond, then what will happen is silicon will have the lowest density. Then it will be carbon. I mean, if you are taking diamond, and then the rest is all same. Then the rest is all same. All right. Yes. Done it. Done. I will do it. But right now, please focus here. Okay. Right now, please focus here. We will do all of these. So is density also clear to you all, everybody? Is density all clear? Yes. Okay. Chalo. Moving on from here, is there anything else? Is there any other physical properties that we are missing out on? Any other physical property that you can think of that we are missing out on, guys? Let me, what I do need is, I need to copy this. Oops. What did I do? Just a second, guys. I need another page. Basically, I need another extra page. So what I'm going to do is, I am just copying this. And where are we? I need an extra page for okay. What did I do now? Sorry, everybody. Just a minute, yeah. Just a minute. Okay. You. Not able to copy, yeah. Okay, I think I got it. Oh, I'm very sorry, guys. I'm a little technologically handicapped, I believe. I can say that, I'm guessing. And then now we come here. I think I got it. Yes. I think I got it. Okay, this is not happening. Totally unfair. Unfair about what? What? Hey, dude, don't do this, yeah? Don't do this. This is on YouTube. You're not on a personal class with me, yeah? You're not on a personal class with me. Come on, don't do that. Please don't do that. Don't do that. Okay, why? Oh God, I need a extra page. This is so unfair. And I'm not able to get an extra page. Can you believe it? Okay, all right. Now what we're going to do is, wow, I cannot figure this out. I guess I am officially technologically handicapped, and I guess I do not know how to run my iPad. But anyway, let's not waste any more time. Let's not waste any more time. Let's get back here and let's get this done with. Okay. All right. I've left so many pages for chemical properties, but not for our physical properties. Chalo. All right, guys. Worrying about organic chemistry. Don't worry. Don't worry. I'll take care of it. Now, I have told you so many times. Anyway. All right. What other physical properties do we have to talk about? I believe that we have to talk about. Oh, yeah. There it is. There it is. Here we have. Melting point. Guys, please check out the melting point once. I'll give you some time here. Please check out the melting point. Do you see that carbon does really have a very, very, very high melting point? Yes. And then you see that it decreases down to group silicon, then germanium, and then tin and lead. Okay, please check it out for tin and lead. Why do you think that there is not a very, very, very huge increase or huge decrease? Why? In fact, there is a slight increase in the melting point when you go from tin to lead. Why? What did I tell you, everybody? What did I tell you? Remember, anytime you see an exception here, especially at the bottom of the P block elements, what will you see? The answer will be, my dear students, lanthanide contraction. Yes, lanthanide contraction. That is the answer. That is the answer. All right, Sai, chill. It's okay. Chill. Don't worry about it. Yeah. All right. Now moving on, boiling point. We again see that for boiling point, it is just increasing normally. By the way, yes. Why do you think that in case of carbon, the boiling point is not mentioned here? Why? Haven't you heard that diamond is an allotrope of carbon? And you tell me, have you boiled carbon? Have you boiled diamond? Can you boil diamond? Nah, that's why. Okay, so that's why we are not writing the boiling point of carbon here, but we are writing the boiling point of rest, all of them. And you can see clearly that how silicon has the highest boiling point, then germanium, then tin, and then lead. Yeah, there is no exception here. Okay, there is no exception here. Cool, everybody. Done. Clear? All right. Yes. Now. Shall we go to our chemical properties? And before chemical properties, can we do oxidation state, everybody? Yes. Oxidation state, everyone. What is lanthanoid contraction? Yeah. F block elements, D and F block elements, you have forgotten. D and F block, have you forgotten? You shouldn't be forgetting it. But anyway, let me tell you, lanthanoids. You know that the F block elements, lanthanoids and actinoids, right? So the F block, basically the F block elements, there the last electron is getting introduced to S orbitals, right? And we all know that S orbitals, right? S orbitals, they have a spherical shape, okay? S orbitals have a spherical shape. P orbitals, they have a dumbbell shape, right? D orbitals, they have a double dumbbell shape, isn't it? And the F orbitals, they have somewhat like this, double dumbbell, but in 3D, somewhat like this, okay? Somewhat like this is their orbital. So basically what happens is the nucleus, if it is here, the nucleus can clearly see if the electron is here, it can pull it. Okay, if the electron is here, it can pull it. If the electron is here, it can pull it, right? So F orbitals, they have a very bad shielding effect. Okay, basically you can consider it like okay, so if I want to make a house, right? If I say that I want to make a house, how do I usually want to make a house? I would like to have my own privacy, isn't it? I would like to have my own privacy. I'll make it with bricks and cement and wall, isn't it? And then there are those people like your, Bollywood actor and actresses. I believe that they actually want paparazzi to come and click their picture. So what do? They make a house with glass. So you making a house with glass basically means that you have no privacy, isn't it? Yes. So what is the shielding effect of glass? None, zero, almost nothing, right? You can clearly see what is happening in the house. So F orbitals being there, they don't have any capacity of shielding. The nucleus can actually see the last electron and it can pull very close to itself, which is why the size also reduces, because now the nucleus, which has the positive, positive charge, can actually pull the electron close to it, and the size reduces, and that is what is called as lanthanoid contraction, or you can say that poor shielding effect, or you can say that poor screening effect, anything that you want to. Okay, this is important for NEET as well. Sailesh, yes, I will make it easily understandable. That is a promise, definitely. But one thing is that I'll do lanthanoid contraction once we're done with the most important chapters and the very basics of organic chemistry, because I need you all to understand organic chemistry. And once you learn organic chemistry, it should be like everything is done. You should never come back and say that I have a doubt in organic chemistry. All right. So don't worry, Sailesh, everything will be done. Okay. Yes, zirconium and hafnium, yes, their sizes are not very different. Why? Because of lanthanoid contraction. So in the periodic table, lanthanoid contraction does change a lot of things, right? Yes, now you will see another reason why you will see that the lanthanoid contraction is again, is again trying to change things a little bit. You will see. But now let's come to oxidation state. So I believe you have understood the oxidation state from the boron family. Do you remember? +3 and +1 oxidation state, isn't it? Very similarly, right here also, you will see that carbon +4, silicon +4, germanium +4, tin +4, plumbum +4. But as you go down the group, the stability of +4 decreases and the stability of +2 increases. Yes? Do you remember this, everybody? Do you remember this? And why do you think that the +2 oxidation state of plumbum, why is it more stable? Because you remember last class also I have told you inert pair effect. And how do we understand inert pair effect, everybody? Basically there is a pair, that means 2 electrons, and the 2 electrons are not available for bonding. They are acting like inert. They are not going to react with somebody, right? So who are these 2 electrons? Where do we get 2 electrons? S orbitals, right? And you remember what is the general electronic configuration? Ns2, Np2. So in case of lead, this s orbital electron, right? This s orbital Ns2 electron, they are not available for bonding, which is why only the p orbitals, they take part, and that is why the +2 oxidation state is more prominent, more stable in case of lead. Yes, bro, mark khaoge, pitti, virtual pitti. I have already answered you that yes, it is important for NEET, but you want me to take your name and then answer, right? I've told you that it is important for NEET also, but that you did not hear. Yes, why are you wasting your time? Understand and focus, know what I'm teaching. Huh? Focus on what I'm teaching you. Learn that. Yes, okay. Acha, now one more exception that you have to understand is that carbon can also show -4 oxidation state. By the way, only carbon can also show you -4 oxidation state. And if you remember, in case of boron also, boron was not able to form a +3 ion. Do you remember? It was not able to form +3 ion. Very similarly, carbon +4 is not formed. Why? Is not formed. Why? Because if you want to form carbon 4, you will have to give ionization energy 1, ionization energy 2, ionization energy 3, ionization energy 4. After 4 ionization energies, you will be able to take 4 electrons away, and then it will form carbon 4 +4, isn't it? Now, if you add all these ionization energies, IE1, IE2, IE3 and I4, it becomes very huge energy. It becomes a really high energy, and that is not feasible for us, okay? that is not feasible for us. So carbon plus 4 is not formed. Why? Because sum of ionization energies are very huge. Okay. All right. Is this clear, everybody? Is this clear to you all? Yes, yes, yes. All right. Acha. Now tell me. Do you see that plumbum does exist in +4 and it also does exist in +2? But we know that +2 is more stable, isn't it? Yes. +2 is more stable than +4, isn't it, everybody? Do you agree to it or not? Do you all accept it? So that means that if I take lead, okay, if I take Pb in +4, then it will definitely try to convert itself to Pb +2. Yes, it will definitely convert itself to Pb +2. And why will it do that? Why will it do that, everybody? Why will it do that, bachos? That's because Pb +2 is more stable. Now, if it is converting from +4 to +2, what is it doing? +4 to +2. +4 to +2. Gaining electrons. What is gaining of electron? Gaining of electron is basically what? Reduction. Yes. Remember, what did I tell you? Oxygen or oil rig. Oxidation is loss of electrons. Reduction is gain of electron. Gain of electron basically means that here reduction is happening. If reduction is happening, do you agree if I tell you that Pb +2 is oxidizing agent? Will you all agree that Pb +2 is an oxidizing agent? Make sense or nonsense, everybody, what I'm telling you? Make sense or nonsense? Tell me, everybody. Will you all agree that Pb +2 is an oxidizing agent just because we know that it is gaining electrons and it is converting itself to Pb +2 from Pb +4? Make sense, everybody? Yes, so this is becoming an oxidizing agent. And very similarly, everybody, what happens to tin is that in case of tin, we see that Sn +4 is more stable. So if you take Sn+2 will lose electrons and it will form Sn+4, which is more stable. Yes, so that means that I can call this as a reducing agent. Am I right, everybody? Yes. And tell me something. Now tell me something, everybody. Do you all understand that Pb +4 is Pb+2 is more stable? Why? Inert pair effect. What is inert pair effect? Because of poor shielding effect of f orbital, the s orbital is no longer available for bonding. Yes, so +2 is more stable, but in case of Sn, +4 is more stable. So coming to a question, please tell me what is the answer. It is because of the inability of ns2 electrons of the valence shell to participate in bonding. That, go ahead and answer me this. Go ahead and answer me this. I've just explained to you the whole thing. Yes, everybody. Go ahead and answer me this. I think you will all be able to do it. Tell me. Yes. Tell me. Yes. Does inert pair effect increase along group or period? Inert pair effect increases down the group because of lanthanoid contraction. Okay. Yes. Thank you, JEE aspirant. Thank you, bacha. Don't spam. Focus here. What I'm teaching you. Yes. Nobody is going to ask you in the question who loves Nabamita Ma'am the most. Okay. No one is going to ask you that question. So focus and study. Yes. Then you come back and tell me that, ma'am, because of you I got this much mark. Love you. I will accept it with all my heart. But right now, focus. Later on, you will only come and scold me. So focus and tell me the answer, guys. Come on, tell me the answer, everybody. Gokul Krishna, well done. You are the first one who has answered. Very good. Sn2 plus is reducing and Pb +4 is oxidizing agent. I have just told you the answer. Pb +4 is oxidizing. Why? Why? Because it has the tendency to gain electron and reduce itself to Pb +2. So it is going to be an oxidizing agent. But Sn+2 has the tendency to lose electron. So it is going to be oxidizing. Yes, it is going to oxidize itself to +4. And that means that it is going to be a reducing agent. Yes. All right. Done, everybody. Are we all clear with this answer? Is there any doubt regarding this answer? Any doubt regarding this answer? Very good, Shakil. Very good, JEE aspirant. I hope that you are also done. Gokul Krishna has answered. Shabari is the new course for JEE Main. No. That's not for. But I'll tell you, no. When we take the live session, I'll tell you, no. Right now, can you please focus here? Please focus here. Okay. All right. Done. Chalo. Now, shall we go to, now let's go to chemical properties. Acha. Let's go to chemical properties. Okay. All right. Now, in case of chemical properties, what are the things that we have to learn? First of all, just like the previous family. What was the previous family, everybody? Boron family. So remember boron family, what was the maximum covalency, everybody? The maximum covalency even in the boron family was 4. Do you remember? Yes. And very similarly, here also you will see that carbon has, you will only see that carbon has maximum covalency, what? 4, only 4, right? Yes. Achha, now tell me something, everybody. Carbon has a very small size. Do you think that it can increase? Have you ever seen carbon forming 6 bonds with fluorine? No. No. Have you seen carbon forming 5 bonds with oxygen? No, it doesn't. The maximum covalency is 4. Why? Small size. Absence of d orbital. If there is no d orbital, how will it expand its octet? How will it expand its covalency? It cannot. Carbon can only form maximum covalency of 4. That means that maximum it can have, max 4 bonds can be formed. 4 bonds can be formed. Right, everybody? Yes, make sense or nonsense? Make sense or nonsense? This is clear? Great. All right. Now, but what will you see is, but you will see that silicon, germanium, yes, then what do you have? Tin and plumbum, they will all expand. Yes, they have the capacity to expand their octet. Okay, have the capacity, but choose, write it down while I'm writing. Write down the notes with me. Okay, yes, silicon, germanium, tin and lead have the capacity to expand its octet. Yes, or in other words, we can say that its octet, or we can say expand its covalency. Yes. All right. Acha. Now tell me something. You must have seen something like SiF6 2 minus, right? Yes, you must have seen it. And you must have also seen germanium Cl6 2 minus. I understand the fact, if you remember, that germanium belongs to 4th period and there is definitely d orbital. What about silicon? Since when does silicon have d orbitals? Since when does silicon have d orbitals? Have you read it? Come back to the electronic configuration, everybody. Did you see that silicon has d orbitals? For silicon, what did we write? 3s2, 3p2. And in the third group, in the third period, since when do we have d orbitals? Tell me. Has this question come in your mind? Has this question come in your mind? And how are you going to explain it? How are you going to explain it? I don't think anybody in the whole of YouTube has ever explained that how come silicon has d orbital. How come silicon has d orbital? But people will say that yeah, silicon has empty vacant d orbital. All the teachers will say silicon has empty d orbital, silicon has vacant d orbital. But how? Why? We don't see. We don't see it. Ram, you are telling me that yes, it is bigger than carbon, definitely. But where did d orbital come from? How do we know that it has empty d orbital? How do we know that? When did we learn that? Nowhere we have seen it, right? Chalo, theek hai. Let me explain this to you, okay? Let me explain this to you. So, the question is, everybody, the question is basically how to identify if any atom or if any element has vacant d orbital. Okay, what is the question? The question is how to identify if an element has vacant d orbital. How will you identify it? Now let's come back to, you remember that chapter where we read about principal quantum number, azimuthal quantum number, spin magnetic number and all of that? Do you remember? Is there anybody who remembers that? Yeah? Do you remember that table? And from that table, everybody, if you remember, guys, you must have seen that. Okay, chalo, let's write it down. Silicon has how many? What is the atomic number? Atomic number is 14, everybody. Yes, if it is atomic number is 14, then how do I write the electronic configuration? 1s2, 2s2, 2p6, 3s2, and 3p2. Done, done, done. 14 electrons are over. 14 electrons are over. So that means from right here, I can see that N, my principal quantum number, everybody, is, what is the principal quantum number, guys? The principal quantum number right here, I can see is 3, isn't it? 3 is the principal quantum number, correct? If 3 is the principal quantum number, now tell me, how do you calculate L? How do you calculate L? Yes. How do you calculate L? L is equal to always N minus 1. Yes. N minus 1 bole to the values of L will be 0, 1, 2. For 0, it means that it is s orbital. For 1, it means that it is p orbital. And for 2, it means that there is d orbital present. And proven that d orbital is present, but it is vacant. But it is vacant. So write down the electronic configuration, calculate what is azimuthal quantum number, calculate what is L, and then you can see if it has the vacant orbital that is required. Now tell me, is this all clear to you? Is this all clear to you that why silicon can form SiF62 minus but carbon cannot? Yeah? Understood, everybody? Yes? Yes, everybody? Understood, guys? Clear? Very good, Gokul Krishna. Yes, you have answered it absolutely right. Yes, you have answered it absolutely right. So this is clear, guys. This is clear. Okay. All right. Moving on from here now. Moving on from here. Okay. La la la. Ay, ay, ay. Thank you. Thank you. That just made me super happy. That just made me super happy. Okay. Acha. Now you must have seen that carbon forms 4 bonds, right? Carbon forms 4 bonds, isn't it? When it forms 4 bonds, what do we call it? We call it tetravalent, isn't it? Yes. What do we call it? When carbon forms 4 bond, it is basically in its tetravalent state, correct? In tetravalent state, if you calculate the number of electrons, you will find that it has 8 electrons. If it is 8 electrons, that means octet is complete. If octet is complete, do you think that it will be accepting electrons or it will be giving away its electron? Nah, not at all. And if that is the case, then what will you call it? Will you call it a Lewis acid or will you call it a Lewis base? None. Because it does not donate electron, it does not accept electrons. So what do we write? We write here, no, we have to change the color, bacha. We have to change the color here and then we will write now. Yes, let's write it with yellow color. Yes, what is it? What did I say? I said that carbon forms 4 bond, right? Carbon forms 4 bond. Yes, when it forms 4 bond, what do we call it? We call it tetravalent. Tetravalent. Ayyo. Tetravalent. Yes, that means that 8 electrons, octet complete. Yes, if octet is complete, it neither accepts electrons, nor does it donate. Hence, it is not a Lewis acid or a Lewis base. Make sense, everybody? Yes, make sense or nonsense? Is this clear, guys? Is this clear? Yes, everybody? This is clear? Cool. All right. Yes. So with this, we are almost done. But now we have to also read about, yes, now we have to read about the reactions. So chalo. So basically, we know, we have this table, but I'm not going to go through the table. Okay. I'm not going to go through the table. Let's understand it on our own. Let me write it down and explain it, and then you can just correlate it with the table so that you have everything, the table can be used like a gist. The table can be used like a gist, a summary of what we have understood. Okay. But I am going to go through it as I am, what am I saying? I've forgotten, sorry. Basically, I wanted to tell you that I'm going to write it down and explain it to you, and then you can go through the table. You can basically just correlate, okay? You can basically, what you can do is you can just correlate. So chalo. First of all, what do we have to read? We have to read reaction with oxygen or reaction with air. Shall we? Shall we? Let's learn it, okay? What are we going to learn? Reaction with oxygen. Now this carbon family, when it reacts with oxygen, do you know what it can form? You must have heard carbon monoxide, carbon dioxide, isn't it? Yes. What does it have? Carbon monoxide as well as carbon dioxide. So basically, when it reacts with oxygen, it can form monoxide, and it can form dioxide. When it forms monoxide, what is the oxidation state? +2. When it forms dioxide, what is the oxidation state? It is going to be +4, right? So this is basically the element with 1 oxygen, and this is the element with 2 oxygen, MO2. Yes? Right, everybody? Is this clear? Is this clear? Acha, now tell me that which one of them will have more acidic character? Which one of them will have more acidic character? And I believe that you all remember when we, in the previous session, I told you that CO, carbon monoxide, is neutral. Do you remember? Yes. So if I write here carbon monoxide, okay, you guys are now going to tell me what is the this thing. What is the acidic or the basic nature of all the oxides that I'm going to write it down, okay? CO, what is that? What is the character of CO? What is the character of carbon monoxide? Very good. Neutral. Yes, what is it? Neutral. Well done. Coming back to the next one. Yes, SiO. Does SiO exist? I told you that SiO, silicon oxide, it does not exist at high temperature. In the last session also I told you, right? It does not exist. It only exists at very high temperature. So once again, what I'm going to do is just going to color it here, okay? Why is it not happening? Yes. This does not exist, okay? This does not exist. Where does it exist? Only exists at high temperature. Exists at high temperature. So we do not know what is the character of this oxide. All right. Now, if I ask you germanium oxide, what was the case of germanium oxide? Do you remember that metalloids? Metalloids, there are only few metalloids that have amphoteric in nature. And which ones are those? It was tin and it was lead, isn't it? Tin and lead, they have amphoteric metalloid oxide. Otherwise, germanium, actually no, yeah. Actually no. Tin and lead are not even metalloids. Tin and lead are not metalloids. There are some metalloids that are amphoteric in nature. And which one was it? Which one was it, everybody? Does anybody remember which one was it? Wow, I have forgotten. Gallium, no. Germanium. Goats are arsenic. Yes, arsenic has a this thing, right? Arsenic has a amphoteric metalloid oxide. Correct. Arsenic has amphoteric metalloid oxide. Then you have what was it? So germanium basically will be acidic in nature. Yes, all the other metalloid oxides are acidic in nature, right? Now what about SNO? SNO is going to be amphoteric, correct? What about PBO? PBO is also going to be amphoteric, right? Now coming here, dioxide. Okay, what about dioxides? Most of them are acidic in nature. Okay, if I have to talk about CO2, CO2 is acidic in nature. Correct, everybody? CO2 is acidic in nature. What about SiO2? SiO2 is also acidic in nature, right? What about GeO2? GeO2 is also acidic in nature. Correct? Yes. But SnO2 and PbO2 once again will be amphoteric in nature and amphoteric in nature. Acha. In the last class, I could not give you a mnemonic on the amphoteric oxides, isn't it? Yes. All right. Cool. Right. Right, everybody? I could not. But today I figured it out. I went through a lot of Hindi mnemonics, and then I found out that there is one that fits here, and that is, everybody, Punjabi. Write it down, everybody. Punjabi song sang by, yes, Alia and Zoya. Zoya Akhtar, you know? Yeah? Yes, Alia and Zoya gave Aishwarya crores. All right. Yes. Now from here, what do you get it? What do you get? Punjabi. So PBO, lead. Okay. Song SB2O3. Okay. Sang SNO. All right. BEO. All right. Al2O3. ZNO. Right. Yes. And then you have gallium, then you have arsenic, and then you have chromium. Any oxides here will be amphoteric. So these are the oxides that are amphoteric, everybody. Now you can remember it. Most of them were in Hindi, but this is the only one that I have converted into English. That is Punjabi song sang by Alia and Zoya gave Aishwarya crores. Can you all remember it, everybody? This is easy peasy biryani tasting. Is this easy peasy biryani tasty? Right? Is this easy peasy? Come on, guys, answer. Are you guys able to understand or not? Chalo, so reactivity with water is done. Yes. Hi, Yamini. Thank you so much. Welcome to the session. Yeah. Acha. Now we have to understand reactivity towards halogen. Chalo, let's learn reactivity towards halogen. Okay. All right. Okay. Are you all with me? Are you all with me, everybody? First, should we do reactivity with halogen or water? Chalo, same only. Let's do halogen. Let's do halogen, okay? Reactivity towards halogen. Acha, bachus, tell me something. Can you all do me a favor, please? When it is 7:20 or 7:30, at 7:30, can you all please tell me in the chat box that, ma'am, it's 7:30 and you have to go to office. Will you please remind me? I have to go to office. The studio was not available, so I'm taking the session right now. But 8 p.m. I have a live session and I have to go to office. Will you please remind me in the chat box, because I'm not looking at the time and all anymore. I'm fully focused in the session. Please, will you remind me, everybody? Will you please do this favor to me? 7:30. 7:30, you guys have to let me know that, ma'am, it's 7:30. You have to go to office so that I can end this session, wrap it up, and then I can go to the office. Will you all do that to me or not? See, nobody is replying. You guys don't love me enough, no? I will also tell you that I don't love you enough. Thank you, Ram Vidun, for answering. Thank you so much. Thank you, Yamini. Thank you, Ram Vidun. Chalo. All right, now, now we're going to do reactivity towards halogen. So, everybody, yes, everybody, what did you see? What was the oxidation state? What was the oxidation state? The oxidation state, there are 2 plus 2 plus 4. So, what can it form? Dihalides and tetrahalides, right? Yes, what can it form? It can form dihalides and it can form tetrahalides. So, let's get back to it. What can it form? It can form dihalide. Dihalide bole to, what is dihalide, everybody? Dihalide bole to MX2. Yes, and it can also form tetrahalide. Yes, what is tetrahalide? Tetrahalide is basically MX4. Okay. Now from here you will see a question, everybody, that PbI4 does not exist. What are halogen? Halogen is fluorine, chlorine, bromine, iodine. And you will get a question. It has come many a times, plenty of times in JEE mains as well as in NEET exam, that PbI4 does not exist. PbI4 does not exist. What is the answer? You will find it out right now. See, check it out. MX2. That means, what is the oxidation state? The oxidation state is +4 here. And what is the oxidation state here? The oxidation state is +4 here. Correct, everybody? Now, we know that carbon actually does not give you a dihalide. Carbon cannot give you a dihalide. Okay. All right. So, let me just write here C None. Okay, no dihalide. What about silicon then? What about silicon? With silicon also you will see that it does not give you a dihalide. So let's just write here none. Alright. Yes, everybody. Moving on from here. Now you will see that from germanium, yes, it does give you GeX2. It does give you SnX2 and it does give you PbX2, which is very, very, very stable. Do you remember? Yes. +2 oxidation state for Pb, plumbum, lead is very stable, right? Now coming to the tetrahalide side, what will we see? In the tetrahalide side, we will see everybody. No, I'm going to go here. MX4 +4 oxidation state, right? Now you will see that C, carbon forms a tetrahalide, CF4. Yes, CCl4, you must have seen. CCl4 exists, isn't it? CCl4 exists, correct? Yes. So, right, you will see CCl4. Then you will also see SiCl4. So, SiX4 basically. SiX4 also is something that we can write. SiX4 will also be there, right? Then what will we see? We will see GeX4. We will also see SnX4. We will also see PbX4, which is unstable. This is unstable. All right. And here, these two are very, very stable. These two are very, very stable, everybody. Yes, these two are very, very stable. All right. Yes, everybody. Now, what did I tell you? That you will not be able to see PbI4. PbI4 does not exist. Why? Why? Because first of all, what happens is that to be able to make 4 bonds, you have to understand that PbX4 is anyway unstable. Because Pb cannot exist in +4 oxidation state. It's not its stable oxidation state. It exists stable in +2 oxidation state. So hence we can understand that PbI4 cannot exist. Apart from this, there are another reason, which is basically that to make 4 bonds, excitation energy is required. Acha. Why did I say excitation energy? Check it out here. When we say NS2, NP2, right? So basically there is S orbital and there is P3 orbital. Correct, everybody? This is how it is supposed to be there, right? So in the ground state, it is existing like this, 1, 2, 1 and 2. But it cannot form bond at ground state, right? It cannot form bond at ground state. So what it has to do is, it has to go to excited state, whereas basically this is excited state. So what it will do is 1 and then you will see that like this, 1, 2, 3 and 4. This is basically the excited state, okay? This is supposed to be the excited state. Now what happens is the excitation energy that is required to form PbI4, that the PbI bond cannot provide. It's not sufficient for excitation. It's not sufficient for excitation and hence you will see that PbI4 does not exist. Am I clear? What did I say, everybody? What did I say? What did I say? First of all, we know that PbI4 does not exist. Yes, does not exist. Reason? Pehla reason. First reason is +4 OS is unstable. Right? Alright. Second is what did I say? Excitation energy required to form bond is not sufficiently provided by PbI. Got it? Is this clear, everybody? Is this clear, guys? Is this clear, everyone? Yes? Alright. Now, there are some questions that you might get from Fayon's rule. Do you remember Fayon's rule? I told you in chemical bonding chapter, just like UCLA, you have to remember SCLA, small cation, large anion. Small cation, large anion will provide you what? Covalent character. Do you remember, everybody? Yes, guys. Do you all remember this? So, chalo. What did I say? I told you Fayon's rule. Fayon's rule. What was Fayon's rule? There are a lot of rules, but Fayon's rule, especially I told you that SCLA you must learn. What is SCLA? Small cation, large anion. Yes, what will they do? They will give you covalent character. Covalent character. Now, in case of this family, the carbon family, do you know what we see? We see that SNF4, okay? And you will see that PbF4, these are ionic. These are ionic. Why? Why are they ionic? We can exactly explain from this Fayon's rule. We can very well explain this from this Fayon's rule. How? What is this? Sn. Sn is a big cation, isn't it? Sn is a big cation, which is just the opposite of the covalent character. Just the opposite of covalent character. Pb. Pb is also big cation, right? Big cation, correct? Big cation, and you can clearly see here that these are what? Small anion. Yes, small anion, exactly opposite to the one that is providing the covalent character. So this will be ionic in nature. Makes sense or nonsense, everybody? Does this make sense, guys? Yes. Does this make sense, everybody? Right? SCLA. But here we can see that it is opposite of the Fayon's rule. So basically this is going to be ionic. Cool? Acha. Acha. Now another thing that is, what else is there? What else is there regarding to this? Silicon. Silicon, have I forgotten anything? SiX4. SiX4, no. Si, say yes. SiCl6. Yes. SiCl6 2 minus. Yes. SiCl6 2 minus. Wait a second. Where did we write that down? Where did I tell you that how Si has this thing? Okay, so here you see that I have told you about SiF6 2 minus. Do you know that SiF6 2 minus exists, but SiCl6 does not exist? Why? Why is it that SiF6? Okay, let's write that down, everybody, here. Okay, let's write that down here. What did I see? I say that SiF6 2 minus exists, not SiCl6 2 minus. Why? Why do you think? Yes? Yes? Why do you think, everybody? Why do you think? That's because you have to understand that, acha, for SiCl6 2 minus, what is the oxidation state, everybody? What is the oxidation state? The oxidation state is +4, right? That means 4 electrons you have taken. After taking 4 electrons, the sizes become very small, right? The size of the silicon is very small. Now you know that chlorine is a bigger atom. Chlorine is a bigger atom than fluorine. That is why chlorine has more electronegativity, isn't it? Now, such a small size of silicon, will it be able to accommodate all the 6 chlorine atoms? Will it be able to accommodate all the 6 chlorine atoms? No. No. So what can we write? We can write here that Si plus 4 due to its small size, cannot accommodate 6 Cl atoms. All right, everybody. Yes, is this clear, everybody? Now, please tell me, is this all clear to you all? Have you all understood? Have you all understood? And I think with this note, reaction with halides. Yes, reaction with halogens is over, everyone. Reaction towards halogen is over. Now we have to read about reaction with water. Is this clear, everybody? I'm going to move away from the board. Please tell me if this is all clear to you all. Have you all understood? Because these are some of the assertion and reasoning questions that may come in your JEE mains. Although I think I have certain PYQs. I do have certain PYQ. See here. Yes. Tell me. E represents an element belonging to carbon family. Okay. Yes. E represents an element belonging to carbon family. Now tell me, stability of EX4 decreases down the 14th group. Is this correct? Yes. We see that plumbum exists in +2 oxidation state, right? Lead does not like the +4 oxidation state. So yes, EX4 decreases down the 14th group. That is true. PbI4 does not exist. I just told you this is also true. Germanium and lead form EX2 as well. Absolutely true, right? But however, germanium has a stable +4 oxidation state and not +2 oxidation state. So this is also true. So what is the correct answer? The correct answer is all the 4. And this is a JEE-PYQ, okay? And this is a JEE-PYQ. Got it? Clear here, everybody? Yes. Now let's go to what do we have to learn? We have to learn reactivity towards water. Shall we go ahead? Shall we go ahead and study reactivity towards water? Chalo. Now let's learn reactivity towards why first element of every group has anomalous, because of small size. Because of small size, absence of d orbital, okay? These are the two major reasons why they act a little different, okay? Yes. User 4, ma'am, when you teach in board. Bacha, no, I'm not going to teach you in board. I'm going to teach you like this, because see, you have to understand that in the office, you do not have, see, in Vedantu, you have a team of 400 plus teachers, and obviously we do not have 400 studios, right? And this is the time when all the channels go live, or they have sessions going on, right? All the teachers, they want studio at this particular time. And anyway, our working hours, our office hours are also in the evening, isn't it? You all are also free in the evening. In the morning too, you go to school and colleges, isn't it? So what happens is there is a huge maramari for studio. So what is the point of me going there and actually taking away somebody else's studio where I have this? I have my, see, I have my iPad, I have my camera, I have my own table, and it is peaceful, right? I don't have to fight with anyone. I don't have to be like, oh, Rama ma'am has booked the studio. Oh, Pratik sir has booked the studio. Oh, Puneet sir has booked the studio. So I have to finish the class fast. I don't have to do that. I can take the class as long as I want to, right? Isn't this better? Isn't this better? I believe that this is better, right? I really like this. I really like this. So I'm going to take the sessions like this unless and until there is an urgent scenario where I have to go to office. For example, for today, that crash course, I have to go to office. So that's why I asked you all to remind me, right? To remind me. Chalo guys, moving on. Now let's do reactivity towards water. What do we have to do? Reactivity towards water. Water. Aaj blue hai pani. Okay. Yeah. So once again, everybody, what do we see? We see that carbon will not react with water. Carbon will not react with water. Silicon will not react with water. Germanium will not react with water. Whoa! The chapter has already become easier, isn't it? 3 elements are not reacting with water. So what do we write? Carbon, silicon, germanium plus H2O, no reaction, okay? No reaction. But what do we see? We see that SNO2 plus H2O, what will it form? SNO2 plus H2O. Ma'am, केएस वर्मा बुक से थियोरी कर सकते हैं क्या? Swami Aditya, basically, bacha, see, KS Verma book is not something that everybody has been telling you. Okay. See, there are 2-3 books that you can buy and not everything. Don't try and get every kind of book. Okay. Swami Aditya, you have to understand that if you want to do physical chemistry, if you ever want to solve any problems from physical chemistry, please use this book. This is from N. Avasthi physical chemistry book. This is for JEE Main and Advanced. Do this. All right. Apart from that, what I will suggest you to do is please get Tattva book. Okay. The Vedantu Tattva book that is there, get that. In Tattva book, you will get 4 different types of or 4 stages of problem solving. Okay. Level 1, Level 2 will be JEE Mains PYQ, Level 3 will be JEE Advanced, Level 4 will be JEE Advanced PYQ, and that way you can get everything done. For physical chemistry, NS Avasthi. For inorganic chemistry, nothing, just NCERT. NCERT pakka se if you study in depth, the table, the in-text question, the theory, everything if you study from NCERT, you will be able to clear inorganic chemistry. And last but not the least, for organic chemistry, you can do MS Chauhan, do the elementary part and then go to the advanced one for JEE Advanced. Otherwise, your Tattva book will again sort you out for that also. Clear hai? Okay. All right. Thank you, RK Singh. Thank you so much. Okay. So SNO2, see, SnO2. Here, what is it? +2 oxidation state. Yes, +2 oxidation state. It will react with water, and then it will go to, made a mistake here. SnO2, it seems. Yes, Sn plus H2O will get you SnO2 plus hydrogen gas. What will it? How will you understand that is hydrogen gas? Pop. Sound. Yes, and here it goes to +4 oxidation state. Correct? Yes, this will be for +4 oxidation state. Now, same way, if I make it react with plumbum, that is lead, what will I get? I will be getting once again PbO. Why will I be getting PbO? Because remember, lead likes to stay in +2 oxidation state and not +4 oxidation state. So it is going to be in PbO. And remember aluminium from boron family? Remember what did aluminium do? Aluminium was not able to react very well with oxygen. And why? Because there was a passive layer. No, there was a protective oxide layer formed. Remember? Protective oxide layer. So yes, here also what happens is protective oxide layer is formed. Yes, oxide layer is formed. Yes, and what happens? Pb becomes passive. Okay, Pb becomes passive. Pb becomes passive. All right, everybody. Yes, basically, see, now you can see me. Now you can see me. Now you cannot. Now you cannot. Right? Yes. Oops. This only rotated. Got it, everybody? Yeah. So this is what is happening. Cool hai? Cool hai, everybody? Yes. Now what we have to learn? Now we have to learn reactivity towards metal. Chalo, I don't think we have much here, but yeah. Is this clear, guys? Reactivity towards water is done. Reactivity towards oxygen is done. Reactivity with halogen is over. Right? And for metal, you can just remember this part. Okay. For metal, actually, you don't have to remember much, but just remember that silicon can react with magnesium and it can form magnesium silicide. Okay. What does it form? It forms magnesium silicide. That's it. That's it. That's it. Okay. Hi, Namita. Welcome to the session. So guys, are we ready to move on towards the catenation and anomalous behavior of carbon? Yes. Are we ready to go? Everybody, are we clear with this? Please write down quickly la 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 in the chat box just so that I understand that you all are clear with it. Just so that I can understand that you guys are all clear with it, everybody. Yes. Are we clear with it? No? Done? No? Nobody is writing la la la. How will I understand? How will I understand? La la la. Thank you so much. Okay. So now whatever table you see, this table is basically the coalition of whatever I taught you. Yes, everything that I taught you is just there in this table so that you can just go through in a glance, right? You can take it as like a short note. You can take it like a short note. Okay. All right, ma'am. Still, it will take how much classes to complete? I think after today, another one session should be enough to complete nitrogen family, oxygen family, and the halogen family. I think chalcogen, pnictogen, and halogen. I think another session we should be able to complete, or maybe 2 more sessions. Maybe 2 more sessions. Okay. See, last year when I taught you, it was the very beginning of my 11th and 12th career, right? So, and I also joined late. I joined this channel also quite late. So there was no time to teach you in detail. But this year I do have the time, right? And I want to do justice to my job. What is my job? To teach you. And I want to be able to teach you properly. So that you, when you come here, you watch this session, you should be able to feel like, yes, ma'am, you have completed everything, right? So that is why I'm trying my best to make sure that I complete everything in detail. And then obviously we will also do the mind map series, and we will also do the session in 1 hour, the session in 2 hours, and all of that we will do, but later on. First, we should learn everything in detail, right? Let's learn everything in detail. So, okay. And you will thank me. Now, after completing all of this, when you go to organic chemistry, bachos, believe me, you will be like, wow, ma'am, this is Makka. Now we know everything. All the basics are clear. All the concepts are clear. You will be able to know how to approach the organic chemistry questions also. So just have some Trust in me. Have some patience. We will clear our JEE exam this year. Okay. All right, guys. Moving on, everybody. Moving on. This question is also done. Now we come to anomalous behavior of carbon. Okay. So first of all, remember I told you why does the first element of any group BCNOF, that is boron, carbon, nitrogen, oxygen, and fluorine, they all behave a little different. Why? Because number one, small size. They have really small size, right? They have higher electronegativity, because why? You have to understand that, see, small size, right? Small size, that means the nucleus is very close to the last electron. That means the nucleus can easily pull the electron that is bonded here. So they have high electronegativity. They also have high ionization enthalpy, isn't it? Why? Because small size, you can't easily take away the electron, baba. The electron will not come out easily. Why? Why? The electron will not come out easily because nucleus is close now. The nucleus is very close. The atom is very small, right? So that is why high ionization enthalpy, high electronegativity, they have small size and they do not have d orbitals. If they do not have d orbitals, how are they going to expand their covalency? They cannot. Yes, right, everybody? Yes. So this is the first reason why they behave anomalous. Why they behave a little different. Correct? Yes. Now what happens is, so just now I told you, everybody, just now I told you that unavailability of d orbitals, right? If there is no d orbital, can they form d pi bond? Can they form p pi bond? Chemical bonding chapter. Do you remember? Chemical bonding chapter. Do you remember? Yes? Huh? No. No, right? Yes or no? Everybody will be like, no, ma'am, we don't remember. If you don't remember, watch the chemical bonding chapter, which is right here. And it has already reached 50,000 views. 50,000 of the students have already watched it. So thank you so much, you guys. You guys are very, very, very sweet. I know that, but let me just show you. If you haven't watched it, watch it so that you can understand everything, okay? D pi bond, D pi bond. I have explained all of this. It will be all there. Where is it? Chemical bonding, right here. See, this is our chemical bonding chapter, everybody. Let me also like it. If you haven't liked it, you should also like it, okay? All right. Yes, you should also like it. Here, right here. This is our chemical bonding. This is our chemical bonding. Watch it if you haven't watched it. Very important, very easy. Once you watch it, then only it will become easy. Otherwise, you'll be like, oh, chemical bonding chapter. Oh, ma'am, how to do this? Right? Okay. Chalo, moving on, everyone. Where were we? Here we are. So because unavailability of d orbital, yes, unavailability of d orbital, can we understand that it has a unique ability to form p pi multiple bond, because ns2 np2 na p orbital is there and p2, so it can form multiple p pi bond. Bole to it can form c double bond c triple bond c double bond oxygen, C double bond sulfur, C triple bond nitrogen. Right? So it can form multiple p pi bond. But rest of the element, that is the heavier elements that you see, silicon, germanium, tin and lead, right? What can they form? They can expand their covalency, na? So they can form not only p pi, heavier elements, that they do not form p pi, they form p pi d pi. What do they form? They form heavier elements. What do they form? They form p pi d pi, or they form d pi bond. Yes, they form d pi. Yes. 2023, ma'am, the playlist made by you. Okay, Ram Vidun, I will do it, but you understand that today also the office is closed. Today is Gandhi Jayanti, right? Everybody is not working. In fact, no one is working. Yeah. Only some of the teachers like us who have very strong dedication to teach the students. We are teaching you. Not everybody. The team is not working. Yeah, we do not have our channel managers, graphic designer. Nobody is working today. It's a official holiday. But you see, dedication. See, we are teaching you. All right. So I'll make it. I'll ask my channel manager. I'll ask our channel manager to definitely do this. Okay. All right. Yes, everybody, are we understanding this? Yes. Now we also know once again letting you know that covalency for carbon is only 4. It cannot expand. Why? Unavailability of d orbitals. Cool hai? Is this clear? Why carbon behaves anomalously? Why carbon behaves a little different? These are all your reasons. You will get the PDF. Don't worry about it. Cool. Now we go to something called as catenation first. Okay, let's understand what is catenation. What is catenation, guys? Before we understand allotropes, or shall we understand allotropes first? I think after allotropes we have to understand catenation. Chalo, let's understand catenation. Catenation is here. Okay. What is catenation? See, in your NCERT it is written that the tendency to link with one another through covalent bonds to form chains and rings. This property is called catenation. And this is exactly what is written in your NCERT. Tell me something. If you have NCERT right in front of you, you can go and check it out, and I can guarantee that this is what is written. This is what is written. So I am going to write down the NCERT. Okay. I'm going to write down the NCERT definition. Okay. Bonding with same elements. Yes, that is the simplest form. But here is the NCERT definition. Okay. NCERT definition is, everybody just writing it down, because you will also probably, no, you will not get it in your board exam. You will not get it in your board exam. That ship has sailed, right? Anyway, what is NCERT definition? NCERT definition says that the tendency to link with, okay, the tendency to link with, what did I say? Link with one another through covalent bonds to form chains and rings. This property is called catenation. Correct, everybody? Yes, this is what it is. Now, catenation is seen in carbon. Carbon has extensively high property of catenation, and then there is silicon, obviously, yes, and then there is germanium and tin also. Lead cannot show catenation. Lead cannot show catenation. Do you remember why? Remember that lead cannot form a covalent bond also. It mostly forms ionic bond. Why? Very large cation. Very large cation. And we know that for covalent character, we need small cation. Lead has a very bigger size, right? So it does not really show catenation. Lead does not show you catenation, whereas you see that carbon has very, very, very high strength of catenation. Okay. Now, you can also say that catenation is actually directly proportional to the strength of the single bond. And you know that lead has very big size, right? So what happens? The single bond is also not very strong. But carbon, small atoms, right? Small atoms, small elements, right? So the strength of the single bond is very high, and that is why the catenation is also seen extensively in case of carbon. Am I right, everybody? Yes. What is happening? Smaller size, the overlap will also be very nicely done, right? So basically what I mean to say is, check it out here. So this is small. This is also very small. Now you see that the overlap will be done very nicely here, isn't it? And that is why we see that carbon-carbon bond energy, the bond energy that you require to break a carbon-carbon bond, is very high. Okay? It is very high. Am I clear, guys? Is this clear to you all? Is this clear to you all? Okay. Now we come to allotropes of carbon. Now I know pretty sure that you all have read about diamond, graphite and fullerenes, fullerenes. But actually, you know, when we come to allotropes of carbon, there are two different types of allotropes of carbon. What did I say? There are two different types of allotropes of carbon, right? Allotropes of carbon can be, everybody, what can it be? It can be crystalline in nature, all right? It can be crystalline in nature, and it can also be amorphous in nature, okay? It can also be amorphous in nature. All right? Now, when I say that it can be crystalline, when I say crystalline, in crystalline, you have diamond. Okay? You will find diamond. You will find graphite. Yes? And you will find fullerene. Okay? Fullerene is also a crystalline allotropic form of carbon. Am I clear, everybody? Yes. Now, when we go to amorphous forms, in amorphous form, have you heard about coke? Have you heard about coke? Yes, you must have. So you have coke. Then, have you heard about charcoal? Yes, charcoal is also this thing. Okay. All right. Then, have you heard about what else is there? Carbon black. Carbon black, have you heard of? Yes, carbon black is also an amorphous form of allotrope of carbon. Okay, everybody, are we all clear with this? Are we all clear with this, guys? Yes? Okay. Now, when we come to diamond, everybody, have you seen the structure of diamond? Have you seen the structure of diamond? And we all know that diamond is very, very, very hard, isn't it? Diamond is very, very, very hard. You know what? Let me try and get this thing. Where is Google Chrome? Yeah. Shall we check out a structure of carbon? No, structure of diamond. है ना? Yes. Let's copy this. And now let's go here. Yes. All right, guys. Now, check out. Everybody, please check this out here. This is your diamond, correct? This is your diamond structure. All right, what is it? What did I say? I said that this is the structure of diamond, okay? Now, in the diamond structure, do you see that each carbon, if I consider this carbon, everybody, or if I consider this carbon, everyone, please check out that this carbon is linked to 1, 2, 3, and 4, right? What is it forming? What is it forming? Each of the carbon is bonded. Each of the carbon is forming 4 bonds, isn't it? It's forming 4 bonds. Achha, if it is forming 4 bonds, then what can be the hybridization, everybody? What is going to be the hybridization? 4 bonds. That means we can very clearly say that it is sp3 hybridization, isn't it? Isn't this sp3 hybridization, my dear students? Yes, this is sp3 hybridization. Now, we know that if it is sp3 hybridization, then what is the carbon, the geometry? What is going to be the geometry of carbon? Tetrahedral. Tetrahedral. Am I making sense, everybody? This is going to be tetrahedral, right, everybody? Yes. And you must have seen here, see, the carbon-carbon bond length, everybody. Do you see it here? Do you see it here? The carbon-carbon bond length is 154 picometer, everybody. What do we mean? What do we mean? That means that this to this carbon-carbon bond length, okay, right here, the carbon-carbon bond length, what is it? It is 154 picometer. If you want, you can learn it. Might come. 154 picometer. What is 154 picometer? Carbon-carbon bond length. This is 154 picometer. Okay. This is 154 picometer. Alright. Now you can clearly see that it is a crystal lattice. I just told you that this is the crystalline type of carbon, isn't it? Haven't I just told you that this is the crystalline form of allotrope? So that means it is crystalline and it forms a rigid 3D network. You can see, right? Does it not look like it is a 3D network? Does it not look like it is a 3D network? You can see, right? You can see, isn't it? Right? And everybody, you know that carbon-carbon bond is covalent in nature. Acha, what is covalent in nature? Covalent in nature, we understand. Do you remember that in the chapter chemical bonding, we have read or we had read that the covalent bonding, what is happening here? P orbital and P orbital. It can form like this. It can form like this. So don't you think that this is directional? It has directional properties, right? It has directional properties, everybody. S and S can form like this. P and P can form like this, or it can form like this. It can overlap like this, or it can overlap like this. Do you remember? So can I not say that it is directional strong covalent bond, directional strong carbon-carbon covalent bond is forming, right? Yes, everybody. So what did I say? What did I say? First I said that crystalline lattice and 3D rigid network, correct? 3D rigid network, isn't it? Yes. And we also know that diamond is the hardest substance, by the way. That is old news, huh? This is actually old news, all right? So I'm not going to write it down, but anyway, it's there in your NCERT, so if you want, you can just read it, all right? It is used for sharpening of tools as abrasive, okay? That is probably there. Used for sharpening of tools as abrasive, all right? Yes. And that's it about carbon. Now see that, have I missed anything? Nothing. Density is very high, 3.51. This is something that you want to remember. All right, and here see 1.9 delta HF 1.9. C double bond C, there is no double bond here, right? And CC single bond C here is your 154 picometer. Clear hai? Is diamond clear, everybody? Any doubts in the diamond? Part? Everything is cleared, everybody, right? Any doubt here, guys? No doubt? Chalo. What is our next one? Next one is graphite. Okay. Now for graphite also, let's bring the picture. Where is our picture? Alrighty, here we have the structure of graphite. Cool. Acha. Now, when you look at the structure of graphite, okay? Are Rohini, it has NTA has not updated about JEE 2024 syllabus only. You are asking about 2025. NTA is very slow. They're not gonna say anything right now. But don't worry, you keep studying, you will rock it. Yeah. Alright, so first of all, do you see everyone that graphite has a layered structure? Do you see everyone that this is layer number 1, right? This is layer number 1, then you see layer number 2, then you see layer number 3. Do you see? It has layered structure, correct? Isn't it? So can I say first sentence, let's write that layered structure. Yes, layered structure, right? And then, thank you so much, Madhuri. Thank you so much. Hi, Tamil. In Tamil language. Tamil theriyad. I do not know. Also, the channel name is JEE English. Bachu. Yes. Pasangalas. Pasangala. That's what Shimon sir says, no? Pasangala. I don't know. Please forgive me if I have used the wrong word. I'm very sorry. I do not know the language. I can only teach you in English. Also, the channel name is JEE English, sweetheart. So I have to teach you in English. There is no other scope of any other language. Okay. All right. All right, guys. So do you see that it has layered structure? And you know what? The layers are held by, okay? The layers are held by weak van der Waals force. Weak van der Waals force. Cool. All right. No, you don't have to say sorry. I was just explaining it to you. Now, this distance, do you see, guys? This distance, the distance between the layer, okay? The distance between the layer, that is, okay, the distance between layers is how much? It is 340 picometer. Learn it, okay? You will have to remember this, okay? 340 picometer. Then, what is the bond length? This bond length, do you see? This bond length, yes, what is the bond length here? Sorry, the bond length is equal to 141.5 picometer, which is lesser than diamond. Lesser than diamond. Diamond had 154 picometer. Here the bond length is 141.5 picometer. Now let's take one carbon here. Okay, if I consider this carbon, do you see that it is only connected 1, 2? Okay, let's not consider this one. Okay, one second. Let us consider. Okay, let us consider this carbon, guys. If I consider this carbon, do you see it has 1, 2 and 3. 3 bonds it is forming, okay? 3 bonds. Acha, if it is forming 3 bonds, okay? 3 bonds, that means what? That means what? sp2 hybridization. Yes, that means that it will form sp2 hybridization. Am I clear? Right? And that is exactly what is written in the table. See, sp2 hybridization, 141.5 picometer. Exactly what I have told you, right? Yes, density is obviously lesser. Density is obviously lesser than carbon because it is not as heavy as carbon, right? We believe we can understand. Acha. Now I just explained that there are 3 bonds it is forming. What about the 4th one? What about the 4th one? What about the 4th carbon? What is the 4th electron doing? Now this 4th electron, this 4th electron, see. The 4th electron, it has an option. It can form bond with this side. It can form bond with this side. Okay. That makes this 4th electron mobile. And while it is mobile, it can jump from one place to another. That means it is delocalized. And that is why graphite is a great conductor of electricity. Once you are saying that doubt hai, samajh nahi aaya. What is it that you did not understand? Please tell me. Please tell me what is it that it's not there. Please tell me what is it that you did not understand. Okay. All right. Let's go here. Yes. So what did I say? Now 3 bonds it is forming sp2 hybridization, right? Yes, everybody. But 4th electron. What is the 4th electron doing? The 4th electron forms pi bond. Yes, forms pi bond and it is mobile. Okay, forms pi bond, but with who? It can form with this side of the carbon or it can form with this side of the carbon, right? Yes, so what happens is it is mobile. It is mobile. That means delocalized. Yes, it can be delocalized. It can move from one place to another. So what will we say? We say that its 4th electron forms pi bond which is mobile. Hence graphite is a good conductor of electricity. Good conductor of electricity. Make sense or nonsense, everybody? Make sense or nonsense, everyone? This is clear to you guys? This is clear? Acha. Now, so you know what? When I kept telling you that I have JRF, right? I'm a research associate from IIT Guwahati, haven't I told you? So one of my summer project was to make a pressure sensor. What is it? I had made a pressure sensor with graphite and dimethyl siloxane, PDMS. Okay, what did I do? I mix PDMS with graphite and a pressure sensor. That means when you give it a stress, what happens is it starts conducting. It starts conducting. Okay, all right. Yes, so I used graphite extensively, and I figured, I mean, it's there in your NCRT also. But if you ever get a chance to work with graphite, you will see that it is slippery in nature. In fact, you can do it. Don't you have a pencil? Don't you all have a pencil, everybody? Yeah, I'm pretty sure that you all have a pencil at your home, right? If you have a pencil, just take the lead part of the pencil, right? Just touch it and try to do this. You will see that it is slippery in nature. Why is it slippery in nature? Now look at the structure, everybody. Just now look at the structure. What is the structure? The structure has layers in it, right? So what happens? One layer slips on the other layer. That is why it is slippery in nature. Okay. All right. So what can I say? I can say that it is slippery in nature. Slippery in nature. All right. It is slippery in nature. Why? Because of this layered structure. Layered structure, and because of the weak van der Waals force of attraction that is there in between the layers. Okay. Now, graphite can also be used as a dry lubricant. Okay. It is used as a lubricant. But at high temperature. Lubricant at high temperature. Now you will ask me, but ma'am, why are we using this as a lubricant? What is the point? We anyway have oil, we anyway have, other lubricants, right? Acha bachcho, at high temperature, oil, what happens when you cook Chinese food? Haven't you seen the Chinese food? They will be using a wok and it catches fire and everything, because Chinese is actually cooked at a very high temperature and the oil catches fire. So you will see that Chinese food has a slight bit of smoky flavor. It is, burnt up a little bit, and you also have a lot of other things like burnt garlic fried rice, burnt this fried rice, burnt onion fried rice, things like this. Why are you burning it? Oil catches fire at high temperature. So that means at high temperature, you cannot use oil. So what will you use? Graphite. Bus. That's it. Done, 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 done. This is all clear, guys. Now we go to Fullerene. Buckyball, Buckminster, Fullerene, Buckminster. Who was Buckminster? He was the one who discovered this, right? Or basically made this, right? So this was Buckminster Fullerene. Buckminster Fullerene was the person who made this. And do you know how he made it? What he did was he took some graphite. Okay, he took some graphite and then he heated it at a very high temperature. He heated it at a very, very, very high temperature in the presence of inert gas. What did he do? He took some noble gases like helium, neon and argon. Yes, he took noble gases, helium, neon and argon, and he heated it at graphite at a very high temperature, and he saw that Fullerene was formed. Now, Fullerene has a football-like structure. I'm pretty sure that you must have Googled it and you have seen it, so I'm not going back and again getting a picture of Fullerene, right? But no, actually it's necessary. Yeah, actually it's necessary to bring you a picture of Fullerene, because we also have to understand the structure. We have to understand the structure of Fullerene. So, let's take this, everybody. Yeah. Okay, okay. Now listen to me very carefully and please do check it out, everybody. Okay, please have a look, because this is important and you need to understand. Okay, so what we were talking about Fullerene. Who made this? This was made by Buckminster. There was a person whose name was Buckminster Fullerene. Okay, he made this. How did he make it? I just told you, heated graphite at a very high temperature. What did he do? In the presence of noble gases, what noble gas? Helium, neon or argon. Okay, in the presence of noble gas, heated graphite at very high temperature to form Fullerene. Okay, now in this Fullerene, what you see is, everybody, please tell me, are you all able to see it? Okay, yes. Do you see that there is a 6-membered ring? 1, 2, 3, 4 and 5, 6. Do you see that there is a 6-membered ring? Okay, do you see that there is a 6-membered ring, everybody? Now tell me something. Do you also see a 5-membered ring? 1, 2, 3 and 4 and 5. Do you see it? Do you see it, everybody? And can I say that it's like a cage, everybody? Can I say that it's like a cage? I can, right? So what can I say? I can say that, okay. First of all, how many carbons are there? Do you know how many carbons are there? There are C60. 60 carbon are there. It looks like a soccer ball. Soccer is basically just a better name for football. Yeah, it looks like a football. We say football. Americans, they call it soccer. So that is why soccer ball. Okay. Soccer ball, you call it, and you also can call it bucky ball, like I just told you, right? You can also call this Buckminster Fullerene, because that was the name of the guy who created it, right? So basically, there are 60 carbon atoms. If you calculate all the points that you see, you will find that there are 60 carbon atoms. Okay. All right. Ma'am, today is very happy. Why? Who is happy? Who? Me? I am not happy. My throat is paining. I want to lie down and take rest. Also today is what? Gandhi Jayanti. And today was the day when Ajay Devgan and his family, they went to that satsang. They had pav bhaji and they came back 3rd October. Tomorrow they will come back to Panji. They had been to Panji today, na? I'm not very happy. Anyway, coming back to it, guys. C60, soccer ball, buckyball, these are the things that you can call it. Now everybody, in this, what did I just tell you? I told you that it has 5-membered ring. There are 5-membered rings as well as 6-membered rings. Okay. Now, if you ask me, ma'am, how many 5-membered rings are there and how many 6-membered rings are there? There are 12 5-membered rings and there are 20 6-membered rings. Learn it if you want. Okay. All right. If that is the case, that means that can I also say that, not can I, but you just have to know it, that there are C single bond C as well as C double bond C. Both are available here. Okay. C single bond C as well as C double bond C, both are available. Now, do you see? Please tell me something. Do you see that? See, here in case of graphite, what happened? There were not this side, there were some carbon atoms which were right on the top, isn't it? Which were right on the top and they are not bonded with anything. Can you see that? These carbon atoms, the top layer, yeah, these are not bonded with anything. These are not bonded with anything, right? And do you see right here? Do you see right here? At diamond, what is happening here? Diamond also, here also you see that there is the topmost carbon which is not bonded with anyone. Do you know what is this called as? This is called as dangling carbon. What is this called as? This is called as dangling carbon or dangling bond. Okay, what do we call it? We call it dangling bond. In this case, however, do you see any dangling bond here? Do you see any dangling bond here? None. None at all. Okay, none at all. So that means that even the one that is right on the top, there is no free valency. All of them are bonded very well. There is no free valency. Okay, there is no free valency and there is no dangling bond. So now again I'm writing that it has a cage-like molecule. Yes, it has a cage-like molecule, and in bracket I'm writing that there is no dangling bond. There is no dangling bond. Crystal clear, everybody? EPBT, please tell me. Easy peasy biryani tasty. Everybody is able to understand or not? Is everybody able to understand? Right? Acha. Now, if I consider this carbon, okay, if I consider this carbon, do I see that there is 1, 2 and 3? 3 bond it is forming. Yes. How many bonds it is forming? C. How many bond it is forming? 3 sigma bond it is forming, isn't it? If it is 3 sigma bond, then what is going to be the hybridization? Just like graphite, it is going to be sp2 hybridization, isn't it? And here also the 4th electron is remaining, isn't it? The 4th electron is still available. So what does the 4th electron do? The 4th electron here is not just mobile. The 4th electron actually gives it aromatic character. It has a smell. It has a smell. Okay. The 4th electron provides aromatic character. Aromatic character. Cool hai? Yes, everybody. Yes, guys. And this is what is written here. Now, please read this table once. Please read this table, everybody. Yes. Oh, thank you so much, notes maker. I'll definitely do that. Yeah. Now, please read this table and tell me, have you all understood everything? Have I explained everything? Yes. Acha, graphite is also thermodynamically most stable form of carbon. Yes. That means even at very high temperature, it can remain stable. Okay. Even at very high temperature, it remains stable. I have explained everything else. Now, please tell me if you have understood everything, guys. If you have understood. Acha, one more thing. One last thing that I have not explained. One last thing. Acha, okay. Please carefully look at this structure. Look at this structure. You will see that, acha, this 6-membered ring, this is 6-membered ring. Do you see that the 6-membered ring can fuse with a 5-membered ring as well as a 6-membered ring? Do you see? The 6-membered ring can fuse with a 5-membered ring as well as to a 6-membered ring. However, the 5-membered ring will always have a 6-membered ring and a 6-membered ring near to it. Understanding? A 6-membered ring can fuse, that means it can have nearby to it, it can have a 5 or a 6. But a 5-membered ring will always have 6, 6, 6, 6, 6. Getting my point? Getting my point? And that is what is written here. See, 5-membered ring is fused only with 6-membered ring. Okay, but 6-membered ring can fuse with both 6 as well as 5. Now, please tell me, is this all clear? But choose, is this all clear, everybody? If you are done with this, only then I can move on to the oxides. Okay. Only then I can move on to the oxides, everybody. Please tell me, have you all understood this? Have you all understood this? And also, let me drink some water. Let me drink some water. See, the class is only going to go on for another 45 minutes, okay? Hi, Venkat. Hello, bacha. The class is only going to go for another 45 minutes. After that, as you know, I have to go to the office, yeah? I have to go to the office. Hi, Venkat Sahit. Welcome, welcome, bachu. Welcome to the session. Welcome to the session. Yes, everybody, is this all clear? JEE का exam day 24th January to 1st of February. Done क्या guys? Yes or no तो बोलो. You guys are such pagloos. You don't even tell me yes or no. See? Now that I'm asking you to chat, now you will not chat. But when I'm not asking you to chat, that time, ma'am, when will this syllabus get over? Hi, Radhika. Hi, Aarti. That time you will do all this. Now that I'm asking you to chat with me, no. Nobody will answer. See? Okay. Thank you, Nagapalli. Thank you so much. Chalo, let's move on. And now we have to understand about carbon monoxide and carbon dioxide. Okay. Then we also have to remember about zeolites, silicates. Oh, sorry. A little more water. Okay. All right. Now let's come to oxides of carbon. Okay. Shall we? I keep it simple. I'm good. I'm good. How are you? Chalo. Oxides of carbon. This is a new topic. Now, what are the oxides of carbon? Everybody knows there is carbon monoxide and there is carbon dioxide, right? So, there is CO2, which is your dioxide, and you have CO, which is your monoxide. Yes, what is it? Carbon monoxide. Correct, everybody? Yes, dioxide and monoxide. Okay. Now, let's read about it. So, everybody, do you know how to create, how to make carbon dioxide? I'm pretty sure what all of you know that you take carbon plus excess oxygen or excess air, isn't it? Excess air or excess oxygen will give you CO2, which is gaseous in nature, right? Yes. But what about carbon monoxide? You take carbon plus you take oxygen, but in limited, okay? Limited amount. If you take oxygen, you will be getting carbon monoxide. Am I not understanding? Yes. Yeah, boy, don't worry about it. Organic chemistry will come. First, let's learn this, okay? All right, everybody. Achha, now another form of how to get carbon dioxide. There is another way to get carbon dioxide, okay? What you can do is you can either combust it with or combustion of carbon. Achha, anything when it reacts with oxygen. Haven't you learned about it? I have only taught you in class 8. Remember class 8, there was a chapter called combustion and flame. In combustion, what is combustion? Something when it reacts with oxygen is called as combustion, isn't it? Yes, it's called as combustion. So very similarly, combustion of carbon or okay, and other compounds, okay, other compounds of carbon, combustion of carbon and other compounds of carbon can produce carbon dioxide, can produce CO2, right? If that is the case, here you will see a reaction, everybody. Do you see here? CH4. CH4. Everybody, do you see CH4? Oxygen. CH4, when it reacts with oxygen, can also give you carbon dioxide. So can I just write that down here? Let me write that down here. So CH4. Very sorry. There is a slight bit of error in the hand-eye coordination today, okay? So what do we have? We have CH4 plus O2. What will it give you? It will give you CO2. Yes, plus obviously water, H2O will come out. Am I right? Yes, everybody. Now here is another reaction. Do you see? CaCO3. Okay, please learn it. CaCO3 plus HCl. If you take, this is basically your lab preparation. What is this? This is your lab preparation. CaCO3. You just have to take calcium carbonate. Calcium carbonate, when it reacts with hydrochloric acid, you will get CO2 plus CaCl2 plus water. So let me write that reaction here as well. What do you get? Lab method is CaCO3, calcium carbonate. Yes, calcium carbonate plus any acid, especially HCl, hydrochloric acid, will give you carbon dioxide plus H2O, alright, plus CaCl2. Make sense? Make sense, everybody? Am I making sense, everyone? Great. Okay. Next, now do you see another time it is written here marble plus, you can heat it also. If you just take marble or if you just take calcium carbonate and if you heat it, this will be your commercial preparation. Okay, this will be your commercial preparation. Just heat it. Remember decomposition reaction. Remember decomposition reaction. So what is happening in decomposition reaction? What will you get? It will just break down, isn't it? It will just break down. So what did I say here? Let me Acha chalo. Let me write it down here. Let me write it down here, guys. Can you see it? Writing it down here, everybody. This reaction, okay? Decomposition. CaCO3. No, not plus. CaCO3, if we heat it, if we just heat it, what will we get? We will get CaO plus CO2. This is another way of preparing carbon dioxide. Alright? Yes, everybody. Cool hai? Cool hai? Achha, now here what is happening is, you take carbon dioxide and if you just add a little bit water, okay? If you take carbon dioxide and if you add water, what do you get? You get here carbonic acid. What is this called as? This is called as carbonic acid. Okay? This is called as carbonic acid. All right, everybody? Yes. Now, this carbonic acid, it is also called as a dibasic acid. It's not called as, it is a dibasic acid. Why? Because what will happen is, it can give you two protons. It can give you 2H plus, H2CO3, right? So, 2H plus will come out. That means that it is a dibasic acid. Okay? It means that it is a dibasic acid. Now, there is one more line about carbonic acid that I'm forgetting. It was something to do with HCO3, H2CO3. Yes, buffer. H2CO3 buffer, everybody. If you can see it, is it written somewhere? No, it's not written somewhere. Chalo, I'm going to write it down here, okay? I'm going to write it down. This is very important, everybody. Please note it down, okay? H2CO3 buffer actually helps maintain the pH of your blood, okay? Buffer helps maintain the pH of blood. What is the pH of blood, guys? It is 7.2 to 7.4, I guess. Please check it out from NCERT. There must be another digit, but I'm just writing 7.2 to 7.4. Okay. This is about your carbon dioxide. Also carbon dioxide, as you can see, it is colorless, odorless, and it is less soluble in water and tasteless. Okay. It is less soluble in water and it is tasteless. Carbon dioxide acts as a Lewis acid. What does it act like? It acts like a Lewis acid, right? This reaction that you see, everyone, this reaction that you see right here, this is basically your photosynthesis, isn't it? This is your photosynthesis, my dear student. You must have seen, right? Carbon dioxide plus water in the presence of H mu. What is H mu? Sunlight and chlorophyll. What do you get? Glucose and oxygen. What do you get? glucose and oxygen, right? So it is used in photosynthesis. It acts like a Lewis acid. It produces greenhouse effect. That means it traps the heat in our earth, isn't it? So these are the things that you have to know about carbon dioxide. Okay, all right. Now moving on, let's learn about a little bit about carbon monoxide. Okay, so here you can see carbon monoxide. See, acha, carbon monoxide, right? Do you know how to make pure carbon monoxide? Pure carbon monoxide can be made by using HCOOH. Okay, HCOOH. What is HCOOH, everybody? What is HCOOH? Can somebody tell me? What is HCOOH, guys? Anybody who can tell me? What is HCOOH? HCOOH. Can somebody tell me? No one will tell me. Ayo, you know this, baboos. You know this from such a very young age. You know this. What is it? Formic acid, guys. Formic acid. Okay. So if you take formic acid and if you add concentrated H2SO4, what you will get is, let's write it down here. Okay. Let's write it down here, everybody. So what are we taking? We are taking HCOOH, which is nothing but formic acid. You know about this. You very well know about this, isn't it? Yes, and then if you add concentrated H2SO4, what will you get? You will get carbon monoxide plus water. And do you know what this is? Do you know what this is? Nothing. You will get carbon monoxide, which is absolutely pure in nature. Okay. All right. But this is your lab preparation. Okay. What we can do is for commercial preparation, there is another way to do it. That is basically you just take carbon and then you add some steam. Okay. Then you add some steam here. What will you get? You will get CO plus H2. And do you know what this is called as? This is called as water gas, or it is called as syn gas. Okay, this is called as water gas or syn gas, everybody. Okay, everybody, clear hai? This is clear. This is your commercial preparation and lab preparation, both are done, right? Another one is, there was another gas, right? Water gas, syn gas, producer gas. Yes, producer gas. Let's write down how to prepare producer gas. C plus O2 plus N2, nitrogen. What will you get? You will get 2CO plus N2. All right. This is called as producer gas. And do you know what? Both of these gases, okay, both of these gases of water gas and producer gas, both are fuels. What are these? These are industrial fuels. Okay, these are industrial fuels, everybody. Are you understanding? Are you understanding? Carbon monoxide, what other thing is there? Okay, carbon monoxide, it is poisonous in nature. Why is it poisonous in nature? So you know what happens is when you inhale oxygen, right? For 2 minutes, let's do that. It will be a good break from my voice also. Let's do that, everybody. Yes. Yeah. So what it does is when you are inhaling oxygen, do you know what you're doing? When you are inhaling oxygen, the oxygen, it goes and attaches itself to the hemoglobin and it forms oxyhemoglobin. But by chance, if you are, by chance, by mistake, if you ever inhale carbon monoxide, and that is why people say, haven't you heard that, in cold areas, especially in Kashmir and etc. places, you are not supposed to burn coal in the closed room. What is happening? Limited air. You are burning coal. Coal, if you burn in limited air, carbon monoxide will produce. Carbon monoxide, when you breathe in, it forms carboxyhemoglobin. Not oxyhemoglobin, it forms carboxyhemoglobin, which is 300 times more stable than oxyhemoglobin, and it can suffocate you and you will die. People will die, basically, not you. People will die, which is why it is called as, which is why it is said to be poisonous in nature. Okay, it is said to be poisonous in nature. Now CO, carbon monoxide, it is used as a Lewis base. Yes, it burns with a blue flame. Now see, why blue flame? Complete combustion happens. Carbon monoxide, right? Complete combustion happens. All right. Yes. No, luxury Hitler. You have to understand that when I was teaching 6 to 8, right, I actually used to teach all the 3 science, physics, chemistry and mathematics. So little bit of basics of bio and basics of physics is also something that I know, but not too much. No, not too much. I'm not great. I'm not like, Einstein's granddaughter or something, but just a little bit basic I do know. Kavita, chill mari bacha, chill mari. Everything will be completed. Don't worry about it. First you learn all these inorganic and physical and all of these basics, and then we will go to organic and you will master it. Yeah, chill. Chill. Don't worry about it. Once we start, there is no stopping. We will keep continuing with it. Okay. Acha. Now, it also, carbon monoxide also forms complexes with metal and metal carbonyls. Remember coordination compound? In coordination compound, we read about it that back bonding happens. That back bonding happens. Do you remember? In that empty orbital of the metal, first what happens? It has a lone pair, so the lone pair is done, and then again the back bonding happens. Yes. So it also forms coordinate complexes. Okay. All right, everybody. It also has the capacity to reduce a lot of metals. Yes, carbon monoxide can also reduce, my dear student. What can it reduce? It reduces almost all metals, reduces almost all metals except alkali metals, alkaline earth metals, and some more. Okay, except alkaline earth metals and some more I'm writing. Okay, and some more. I can't remember which ones are the ones. So just and some more. Cool. Hey everybody, is this clear, guys? Now what we have to learn is we also have to learn about the structure of carbon monoxide. What is the structure, guys? Structure will be this: C double bond O. Right now we know that water has a lone pair, and you see that water has what? Water has 6 electrons, right? So 6 plus 2, 8. Now water's octet rule is getting completed, right? The octet for water is getting completed, but what about carbon? Carbon's octet rule is it getting completed? 4 plus 2, no, 6 only. It is not getting completed. So what will happen is this lone pair that is there with the oxygen, it will be donated to carbon. Now, because this is forming a coordinate bond, remember in the last session also we read about it. So what it will form is C triple bond O right here. This will have a plus sign, this will have a minus sign, right? This will have a minus sign, this will have a plus sign. So this is how you can change the coordinate to covalent bond. Done. Clear, everyone? Yes, everybody? Clear? Good. All right. Now we come to carbon dioxide. Yes, carbon dioxide has basically, it forms C double bond O like this, C double bond O like this. Right? Now, obviously, oxygen will have lone pair, oxygen will have lone pair. Now, don't you think that in organic chemistry you will learn, right? Yeah, same like back bonding. Yeah, same like back bonding. No, not this one, not this one. Back bonding was here. Back bonding was CO forms complexes with metals, right? CO forms complexes with metals. That was back bonding, okay? Metal carbonyls, they have back bonding. Not here, not here. Please go and watch the coordination compound. You will learn about it. Chalo. Moving on, everybody. Now here in organic chemistry, don't you know that you read about something called as resonance structure? Yes, resonating structures, resonance structure. You read about this, right? So here what will happen? This one will come here and this one will go here, right? And the opposite of that can also happen, isn't it? Opposite of that can also happen, correct? Like from here, this can come here and this will go here, right? So it has canonical forms and everything basically, right? And baki everything is done basically. Yeah, baki everything I have taught you. Acha, it also has 2 sigma bonds. It also has 2 pi bonds. Okay. And what does it have? So you can clearly see that this has sp hybridization, linear shape. Is there anything that is left? Is there anything that is left? Nothing, right? All done. Now, shall we go to compounds of silicon, everyone? Can we go to compounds of silicon? But choose, we have to do it faster, huh? I only have another 20-25 minutes. I only have 25 minutes. In 25 minutes, we have to complete carbon family, everybody. After that, I have to go to office, like I told you. Chalo. All right. Silicon dioxide, everybody. Now, silicon dioxide. Do you know what it is called as? It is also called as C. Clearly, you can see here covalent 3D network solid, right? Covalent 3D network solid. Do you see it? That means this is also called as 3D silicate. This is called as 3D silicate. Okay. All right. After this, now you must have seen that when you buy a new thing, right? maybe a bottle, a water bottle, a Milton flask, or a shoe, new shoe, or something like that. And when it gets parcel to you, have you seen those chotu chotu packets which you shake it, chat, 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 sound comes? Yes, what is there? What is there in it? That has silicon dioxide. Okay, it's silica gel. That silica gel, what it does is it is a drying agent. Okay, it is a drying agent. It does not let moisture be there. Yes, it absorbs the moisture. Okay, all right. Now, what is this commonly called as? Commonly, it is called as silica. Okay, all right. Now, what happens here is if you actually see the picture of silica, right? If you actually see the picture of silica, do you know what you will see? You will see like this: SiO, SiO, Si, yes, O, Si, then O, and then Si. So 1, 2, 3, 4, 5, 6, 7, 8. 8-membered ring. What is this? This is a 8-membered ring, everybody. Okay, 8-membered ring. Clear? All right. Yes. Now this silica, this silicon, it has 4 sigma bond. If it is 4 sigma bond, then what will it form? sp3. sp3 means tetrahedral, right? sp3 means tetrahedral. Am I correct, everybody? Absolutely right. Yes. Now this Si and O bond, it is very, very, very strong. It is so strong that is actually almost non-reactive. Because of such a high bond enthalpy, it is almost non-reactive. But there are 2 reactions. Chemistry, mystery, exceptions, you can't let it go, right? So there are basically 2 reactions only, and that is, one is with HF, okay? One is with HF. What forms? SiO2 with HF, it will give you SiF4, okay? It will give you SiF4. Now, in SiF4, if you add another time HF, then it will form hydrofluorosilicic acid. What does it form? It forms hydrofluorosilicic acid, okay? Now, if you add SiO2 plus NaO, it's sodium hydroxide, then it will form Na2SiO3 plus water. This Na2SiO3 is called sodium silicate. What does it form? Sodium silicate. Okay. All right, everybody. Yeah. Cool hai? Cool hai? Acha, now this is your crystal, right? This is your crystal. Do you know that actually if we go through compounds of silicon, right? In case of compounds of silicon, we will see something called as silicates, and silicates are actually crystalline. Okay, silicates are mostly crystalline. However, amorphous form of silica, okay, amorphous form of silica is called as Kisgar. Kisgar, yes. What is it? Amorphous form of silica is Kisgar. Cool? Alright. This is also there in your NCERT. Chalo. Now we come to silicates, everybody. Acha. If you see silicates, what is it that you are seeing, everyone? What is it that you are what is it that you see? Huh? So here, what do we have to see? Binary compounds, that means, why is it called? It is called as a binary compound. Silicates are called as a binary compounds. What is the difference between silicon dioxide? That is, what did we read? We just read about silicon dioxide or 3D silicate. What is the difference between 3D silicates and normal silicates? The only difference is that was SiO2 and this is SiO4 minus 4. Okay, that is the difference. All right, that is the difference. That was SiO2. This is SiO4 minus 4. Correct? All right, everybody. That is the basic structural unit. Now, in silicates, you have different examples. What are the examples? Feldspar, zeolite, asbestos, mica. Mica. Does anybody play keyboard or harmonium? Any of you play keyboard or harmonium? Yes. So that white, this thing you see, those white keys that you see, right? Those are actually made of mica. Or you might have seen it on your wardrobe. On your wardrobe also sometimes the white part that you see, that is also called as mica. Okay. All right. Yes. Oh, no problem. No problem. No problem. Thank you, Ram. Thank you so much. Yes. Okay. All right, everybody. So these are mica, asbestos. Asbestos, you might have seen that false ceiling. A lot of people, they have false ceiling, right? Just to decorate their house and put all those lights and everything, they have false ceiling. The false ceiling is made up of asbestos. Okay, all right, yes, cool. Now in this what happens is the SiO bond, the silicon and the oxygen bond that you see, right, it can be considered as 50% ionic and 50% covalent. Why? Because the electronegativity difference is actually very less. The electronegativity difference is very less and it is just about 1.7. Okay, all right, it is just about 1.7. And the most important man-made silicates that we know, I have given you the example, glass, cement, right? These are all examples of silicates. Okay, all right. Now this is a tetrahedral unit, may exist as discrete units. Forget about all of that. You don't have to remember all of this. Acha. There are different types of silicates, by the way. Okay, there are different types of silicates. Okay, what are those? Different types of silicates are, you must have read about it, isn't it? Or you must have heard about it. Pyrosilicate, cyclic silicate, chain silicate, orthosilicate, isn't it? So this SiO4 minus 4 that we read, yes, SiO4 minus 4, this is actually called as orthosilicate. Okay, what is it called as? Orthosilicate. What is the diagram of orthosilicate? You must have just read it, that this, there is one O and here is another O, right? So all of them have minus, minus, minus and minus charge, isn't it? Right? This is sp3 hybridization and tetrahedral in shape. Am I right? Everybody? Absolutely. Now next we have SiO7. SiO7 minus 6. That is called as pyrosilicate. Okay, pyrosilicate. Now, pyrosilicate is very simple, very easy. Just check it out, everybody. You will be able to learn it. See, pyrosilicate is basically SiO minus, O minus, O minus, here minus, minus. And this O, we will just connect it with another unit. Okay? With another unit. See? So, 1, 2, 3, 4, 5, 6. 6 negative charge and this O is connected. Okay? And this O is connected. All right, then you have cyclic silicate, chain silicate. Forget about all of that right now. Let it be. Now this silicon that you see, yes, this Si, or right here you must have seen, right? Right here, Si. What if we start replacing some of the silica to aluminium? What if we replace some of the silicon atoms with aluminium? What are we going to call it? What are we going to call it? We are going to call it as aluminosilicate, isn't it? We are going to call it as aluminosilicate. Yes? Yes, everybody? So, zeolite is an example of silicate. Yes, zeolite. I just told you, remember, silicates. What are the example of silicates? Feldspar, zeolite, asbestos, mica, isn't it? Yes, I've just told you. So, zeolite is an example of a silicate. This zeolite is also called as aluminosilicate. Clear hai? Clear hai? Now, when you read this chapter, hydrogen, we will read hydrogen, okay? After some time later, we will read about hydrogen. In that chapter or in the S block chapter, we will read that it is a shape selective catalyst, okay? It is a shape selective catalyst. There is also another example of zeolite that is called as ZSM5. ZSM5, yes, ZSM5. We will read about ZSM5. Yes, it is used to convert. See. It is written somewhere. See, it is written. ZSM5, it is used to convert alcohols directly to gasoline. What is it used to convert? Alcohols to gasoline. Okay. All right, everybody. Done, everyone. Cool hai? It is also, see, I just told you, right? You will read about it in the hydrogen chapter. Water, when we read about water, very well, that time you will read. See, it is used as an ion exchange softening of hard water. Yeah, this example is also there, okay? All right, acha. Now, here, one thing is written that is acquires negative charge. No, here, acquires negative charge. Why is it acquiring negative charge, Bachu? Why is it acquiring negative charge? Because tell me something, the Si was in +4 oxidation state, isn't it? The Si was in +4 oxidation state and we are replacing now it with Al +3 oxidation state. So, if we are replacing Si +4 to Al +3, what will happen? there will be negative charge. Yes, negative charge is acquired. Negative charge is acquired. Easy peasy biryani tasting. Please tell me, is everything clear to you? Is everything clear to you now from here? Yes, everybody. Is this all clear, guys? Is this all clear? Okay. Now, finally, we have the last part, that is silicones. Okay. Last part is your silicones. Okay. What is silicone, guys? What is silicone? Chalo, let's easily write it. Silicone actually has a repeating unit. It is a what do you call it? Polymer. Polymer, you know what is polymer? Polymer consists of monomer repeating units, right? So it has a repeating unit, and the repeating unit is R2SiO. R2SiO is your repeating unit, bachchos. Okay, this is the repeating unit. All right. Yes, and it is called as a organosilicon polymer because it looks like an organic compound. See, you are starting off with your organic chemistry little by little right here. Okay, what do you have? This is called as organosilicon polymer. How does it look like? How does it look like? What is this R? The R can be a methyl group, right? The R can be a methyl group. The R can be an ethyl group, right? But let's just check here. See, Si, you will have Si, right? See, Si, and then R or. Let me not write R here. Wait a second. Let me not write R here. Let me write it as Me. Yes. Now what will happen is, see, OH and actually OH, right? But here I wrote O, R2SiO as the repeating unit. But now you will understand that why did I write O? Tell me something. If I have another unit of this, okay? If I have another unit of this, please check it out. Another unit of this, see, SiMeMeOH. Now tell me something. When you see these two units, don't you think that H2O will come out from here? H2O will be released, and the moment you see that H2O has come out or the removal of water has happened, that means now I can call it as a condensed polymer. Yes, now I can call it as condensed polymer, and now I can write it as SiMeMe. Here you will have O, here you will have O, which will be connected with another of the same unit like this, and this will continue, isn't it? And this will continue, correct? Yes, this will continue. So this condensed polymer becomes our silicone. Am I right, everybody? This condensed polymer is basically nothing but our silicone. All right, everyone. Is this clear, guys? Is this clear? Now all the things are written here. Okay. Now all the things are written here. You can just go through it. Okay. You can just go through it. Okay. See, here it is written. Achha, now tell me something. You probably are asking that, ma'am, how did we get this? How did we get this part? This unit, how did we get? To get this unit, here is your reaction, everybody. Do you see? Do you see the reaction? All you have to do is, everybody, you have to take CH3Cl or RCl that I was just explaining, RCl. This RCl is nothing but CH3Cl. CH3Cl plus Si if you take, and in the presence of copper powder, if you heat it, then what will you get? You will get this unit. You will get this unit that I was just talking to you about. This unit you will get. Okay. All right. Apart from that, is there anything else that I have missed out on? The chain length of the polymer. Now, if you want to cut down on the chain, right? See, I told you, remember here, see. It will keep getting continued, right? Yes, the condensed polymer, it will continue. The units will be repeating and repeating. So you might want to cut it down somewhere, right? You would want to cut it down like bus. I don't want it to be longer than this. Right. At that point of time, all you have to do is you just have to add this CH3SiCl, and that will block the end. That will block the end. All right. Yes, everybody. Now, one question, and then I'm going to let you all go. We will start from nitrogen family in the next session. That will happen tomorrow. Yes, tomorrow we will do Tomorrow we will do nitrogen family and oxygen family possibly, but I hope that I have a little more time. Tomorrow I don't have to go to office, so I think I'll be able to complete it. Chalo. In graphite, electrons are, you tell me guys, localized on each carbon atom, spread out between the sheets, localized on every third carbon atom, or is it present in anti-bonding orbital? Ayyo. What is the answer? Anybody who can answer? Very easy, very peasy. That is, it is spread out between the sheets. Option B is the correct answer. All right. And finally, we have to go to the group 15. That is nitrogen family, but that we will start in the next session. Today, I will have to let you go here. As you all know, I also have to go to office. From tomorrow, we will start with group 15 elements. So please remember it, everybody, and I will see you tomorrow. Tomorrow, what time? Tomorrow, I will see you once again at 4 p.m. And tomorrow, we will try to complete at least nitrogen and oxygen family, and then the fluorine and the noble gas family, we can do it later, or we will try and see if we can complete it, okay, tomorrow. All right, now that you have understood all of these, it should be a little easier for you to complete your, nitrogen and oxygen. That is nitrogen, halogen, and chalcogen family we will complete, and the noble gases are easy. Oh no, we also have to learn about a lot of xenon compounds. Yeah, we all will also have to learn about a lot of xenon compounds. But anyway, that was all for today. I think I'll see you all tomorrow. Yes, see you all tomorrow. Not I think. I will see you all tomorrow. Yes, with this note, everybody, tara, bye-bye. Thank you so much. Dhanyavadagalu for watching it. You guys are the best. Stay tuned to the channel. Keep coming up for more and more session. And pakka promise your JEE will be cleared. But you have to stay tuned and you have to come for the sessions, okay? 50% of the work, if we do 50% of the work, you will also have to do. We can bring you questions, we can bring you the concepts, but you will also have to study with us. So with this note, lots of love and tara bye-bye. I'll see you very soon. That is tomorrow. Tomorrow at 4 p.m. or I'll announce the date and announce the time in the Telegram channel. So don't miss it. It'll be very important.